again for coming in.
All right. And should I just start or?
Well,
Yeah.
I'll just say, everybody, that good morning and welcome to another week of the summer school. And we're very grateful to have Christopher Aubin here from Fordham University, and he's going to talk about data analysis, which is an important part of doing Lattice QCD. Okay, go ahead, Christopher.
All right. Thank you, Joel. So let's see. Let me go ahead and start sharing my screen. Welcome, everybody. So at least I do know one person in the audience, and I may have to pick on him because he's he's had me before in plenty of classes, and now he gets to have me one more time as a graduate student. Um, so yeah, as Joel said, I'm Christopher Aubin. Yes, the proper pronunciation is Aubin, but like any good American, we've bastardized our name. And I'm going to spend this lecture and the next two lectures on data analysis in Lattice QCD. Um, and I'll say right now, if ever you have questions during the entire lecture, please raise your hand or send a message to the chat window. I would prefer it if you ask the question out loud, if you unmute yourself, just so that I don't feel like I'm just talking to a blank wall. Um, but if you feel uncomfortable asking questions out loud, be sure to just use the chat window, and I'll try to notice it if I can. Also, if I'm cutting out or if I freeze, the standard online problems, please be sure to let me know. And so I'm going to spend today talking about, as we said, data analysis in Lattice QCD. Or better but longer title is, now that you've spent months or years performing these simulations, how the hell do you understand what you just did? And that's why this is such an important aspect of Lattice QCD. And quite honestly, any numerical field, just like it is an important aspect of any experimental field. So let me just start about some details about myself. First of all, if you want to refer to me, do not refer to me as Professor or Dr. Aubin. Call me by my first name, and that is Christopher, not Chris. I'm very annoyingly particular about this, partially because most people with my name go by Chris, so it makes me a little bit more distinct, and I like to be different. Um, my preferred pronouns are he, him, his, so I encourage you to please share with me your preferred pronouns if you'd like. And I put up these maps because I just like to show you how much I've moved around, just to sort of give you an idea of maybe what's going on in my head. I was actually born in Germany. My dad was in the army, and so I was born actually back when it was just West Germany, this portion. Um, and then we moved to Georgia, and then back to Germany. And when my dad retired from the military, we moved up to Maine, and that's where I spent the latter part of my childhood and graduated from high school. I got my Bachelor of Science in Physics down at the University of Dallas in 1999. Um, Moved a little bit further north to go to Missouri, to go to Washington University in St. Louis to get my PhD in 2004. Working on some of the stuff that I'm actually going to talk about today. I did my first postdoc here in New York City at Columbia. Then I moved down to Williamsburg to the College of William and Mary for my second postdoc. And that's actually, both of those places are where I have overlaps with Wei Wen Lin, who gave lectures about a week and a half ago, you've all heard from. She was a graduate student when I was a postdoc at Columbia, and then she was a postdoc at Jefferson Lab, which is right near William and Mary, when I was a postdoc. I've been at Fordham for about 10 years now. I got here in 2010, which is right here in the heart of the Bronx. Go Rams. And now I'm an associate professor here, both doing a lot of teaching because we have no PhD program at Fordham, but we have a pretty good undergraduate program, I like to think. And obviously, as you know, my research is focused on Lattice QCD. Largely, it's focused on areas devoted to a lot of what we'll talk about today, understanding the errors and the uncertainties that are inherent in the calculations, in the simulations that you do. As you may know already from the first slide, mild obsession with dogs, and so my dogs will show up in the talk in my lectures a couple of times. I'm not going to apologize for that. So now let's sort of get to the crux of today's lecture. Just like with experimental physics, we need theory, right? Theory is an important aspect of the field because when you're trying to understand what you're doing experimentally, you need some sort of theoretical model to understand what you just did. And this is a lot of times, I don't want to say ignored, but not really focused on, at the undergraduate level, because it's just sort of seems obvious. You do these calculations and derivations in your physics lectures, and then you might go to a physics lab and do some little test to test the theory, but it doesn't always it's never always clear how those two connect, right? But for example, if you're dropping an object to try to test the free fall acceleration due to gravity, you need a model, right? You need theory to come to the rescue to understand what you've done. And the same thing is actually true with numerical simulations. We're going to do all this simulating, but when you get these numbers out of the machine, what does that actually mean? What do they mean? And what do they tell us about what we can understand? Now, you, of course, had a lot of lectures on Lattice QCD and some basic data analysis. So Wei Wen, a week and a half ago, had you work on some effective mass plots and understand that sort of stuff. And you could sort of think of this as a continuation of that, okay? Rich Brower, of course, talked about curve space times, and this past Friday, Chris Monahan talked about sort of Lattice QCD as an overview in terms of the simulation side of everything, okay? So this is sort of the aftermath of all of that. This is not just after the simulation, what Ben talked about, but also even beyond that. And so that's basically what today is going to be about. Okay, so what is the plan? This first lecture is going to be maybe about half the time spent with me blathering on and lecturing with some details about nonlinear fitting. For many of you, this may bore you, as it bores Loki, because it may be a review. And if that's okay, then you can just sit tight and enjoy the fact that you know something that maybe others don't. But for many of you, this may be very new, or at least maybe just, again, a nice refresher for what you've sort of touched on in the past. And what we're going to do today is then extend what you did with the effective mass plotting with Wei Wen and actually extract masses from correlators in Lattice QCD. Okay, so that's going to be basically the crux of today for the first part this morning, and then for the entire second lecture. So actually, the second lecture is not a lecture at all, because what we'll do is we'll stay all logged in, and I'm going to give you some handouts and some data and some code for which then apply. Okay, and I'm hoping that between the second half of this morning and then during the second lecture this afternoon, you'll be able to get a lot of experience in doing a lot of these and understand what's going on. Will be so the second lecture, the third lecture of the day, will be what you do after that. Once you've actually extracted those masses, well, now what? Because there are still problems that will arise when we try to understand those things. Okay. So, okay, about the plan. So as I said, as you see, this is the so I'm not going to state all this again. So let's do a quick review. Okay, I've got just a couple slides that go over what you heard about with the previous Lattice QCD lectures. This is my only slide on thermodynamics itself. Okay. I always like to review it. I think it's always good to review it because it's likely that I'll say than others have. But as you know, the strong interactions are called that for a reason. They're too strong for perturbative methods to hold, unlike the weak interactions or quantum electrodynamics. And really, QCD could be thought of as a mnemonic device just taken way too far. We say that all of the quarks come in three colors. They come in red, green, and blue, and they're just called colors. There's not really a color of these quarks. Anti-quarks would have anti-color, and so the anti-color of green would be magenta, and anti-blue is yellow, and anti-red is cyan. Every physical state, for some reason we can't quite understand, but we state it to be true and seem to be true if we externally colorless states. And so you can think of this using the color wheel as adding different colors of light, not pigments, right? So when you add red, blue, light, you get white light. If you add magenta, yellow, and cyan, you get white light. So those are your baryons that are made up of three quarks, or the antibaryons made up of three antiquarks. Think of the mesons made up of a quark-antiquark pair. So green and magenta, white, blue and yellow, white, and so forth and so forth. Ones of the um, of the interactions also have color. They come in color-anticolor pairs, which is not really relevant for our discussion. But that's one of the other reasons why this theory is so difficult to solve. Those gluons interact with each other quite strongly as well. So we have a highly nonlinear theory. Okay. And so since we can't solve this analytically and we can't solve it perturbatively, we go to the lattice. Okay. And there you go. There's all you need to know about QCD for my purposes. Now, again, I'm not going to go with the whole background of lattice QCD because you had a lot of that on Friday and with previous lectures. And I'll talk about a few applications that will be relevant for today's lectures. Okay, and so again, as you know, we discretize space and time on a grid, a four-dimensional grid, where all of our quarks, these purple guys right here, are going to sit on the sites. Okay, and then the gluons will live on the links. They're going to live on the links between the quarks, and so they're going to cause the interactions between the gluons. So these two quarks are going to be interacting via this gluon that's sitting on these links. Okay. And again, you heard about that a lot before, but let's say we do a whole calculation, right? We know that we take this calculation, we go to Euclidean space, so we can't calculate everything on the lattice that we could in Minkowski space because we're not living in real time anymore. But there are a lot of things that we can study. Okay, the three that I'll talk about right now are really hadron masses, which you've again had some experience with already, hadron properties, and then the search for new physics. That's really the exciting, sexy part of the field, right? When you can look for new things. And some of this that I'm showing the older results, but they're just for illustrative purposes. So in addition to hadron masses, we could calculate properties of hadrons. And this is often useful when, say, you've got a particle. In this case, this left-hand plot here is relevant for the delta plus plus baryons. The delta, right, heavier cousin of the nucleon, and it lives for roughly 10 to the negative 24 seconds when it's created. So it doesn't live very long. And so it's very hard to measure properties of the delta. However, if we trust what we can do with Lattice QCD, which means we have an understanding of all the uncertainties and errors, then we can do a calculation for a property of the delta baryon and then use that as our known value of that instead of using experimental results. So what I'm showing here in this left plot is as a function of the magnetic field, the magnetic dipole moment of the delta baryon. And so the magnetic dipole moment is basically how a charged particle can interact with a magnetic field. And if I have a magnetic dipole moment when I'm in a magnetic field, then I'm going to get an energy of mu dot B, okay? Plus or minus mu dot B, depending on the direction of the field relative to the magnetic moment. So what we can do on the lattice is put in a background magnetic field, which is what this horizontal axis is, and then look at the mass shift. The mass is really just energy of our particle, just at rest. And of course, that energy is going to get shifted by the magnetic dipole moment dotted into the magnetic field. And when we do that, what we have here are we have three different masses for the pion masses. Those are the input pion masses. And you can see they're very heavy, right? The real pion is around 140 MeV. So these are all unphysical pion masses. And the idea is that we will take these fits, and these are fits that were done about 10, 12 years ago, to zero magnetic field to sort of see what would happen, what we would get for the magnetic dipole moment. And there's a theory that we can write down that we've worked with that would say that the limit of this expression as it goes to zero, as the horizontal axis goes to zero, is the magnetic dipole moment of in this case, the delta plus plus. And what I pulled out here is the current particle data group value for the magnetic dipole moment of this particle. Now, at the time of these simulations, it was ranging from 3.7 to 4.2. Okay, so there's a nice wide range. But if you look at all these different numbers, right, this most recent result is fairly precise comparatively. There's a wide range of measuring this experimentally because it's a very hard thing to do. Okay, and with a quantity like this, if we could get even 5 or 10% uncertainty in the final result, then that would help us understand something about a particle that we may not be able to measure experimentally. In a similar vein, this middle plot here is looking at the anomalous magnetic dipole moment of the muon, a lepton, the heavier cousin of the electron. And again, there's a lot going on in this plot. I'm not going to talk about numbers or results. I just want to sort of state that this is looking at two, we say, where the magnetic dipole moment is some g factor times the gyromagnetic ratio times the spin. So we're looking at this g value here. And this green vertical band is the experimental number with its uncertainties. Okay? And that's currently as of the latest Brookhaven results. And this is an experiment that's now running at Fermilab, which will get hopefully more precise results soon. All of the other points you see are theoretical points. These red points in the middle are phenomenological points. These upper ones are a lot of different lattice results for this quantity. And we're going to talk about this calculation later this afternoon. So I'm not going to worry about it now. All that you need to look at is comparing these lattice points to the green band. If these lattice points plus their errors are sufficiently outside of the blue band, we would say there's no new physics. Okay, that within acceptable uncertainties, theory and nature agree with each other. And so you can see the red points, these have been worked on for decades. There's always a little bit of a tension between the theory and experiment. They're just outside the realm of agreement. So if we could pin down a lattice result much better, you can see this RBC UK QCD number down here is right on the overlap, but with really good small uncertainties. And we could pin down the experimental number even better. This might be a signal that there is definitely some new physics that we have not accounted for in the standard model. And that is something that's very exciting. Okay. Finally, and this is more of a technical point, there's another place that we could search for new physics using the kaon mixing parameter, BK. And this just gives us the amplitude for a neutral kaon turning into a neutral anti-kaon. And again, this is an older set of data. This is still being done in precisely. This is actually a useful result because you can see, again, all of these data points with the error bars, those are lattice results. Okay, and these numbers are extracted not in the same way as you would extract a hadron mass, but in a similar way. So you again have some experience with that. But these are all performed at unphysical quark masses, just like these numbers for the delta magnetic moment were. And the key is I want to extrapolate to the physical point, which in these weird units is around here, okay, where this asterisk is. how do I do that extrapolation? Also, these are done at two different lattice spacings, and so I need to know how to incorporate that. And it's not just a simple linear fit. You're not just going to assume, oh, let's fit a line because that's the easiest thing to do. Because actually what we do is something much more complicated, and you can see that if you look to the left of these fit curves, there's a little bit of curvature, right? So this is not a straight line. And in fact, I'm not going to show it, but it's a rather complicated function. That is going to be this, not this particular quantity, but that idea of once we've actually fit the data to get these masses, which you're going to do after I finish this morning, but we then need to know how to fit the fit results. And that's going to be the third lecture today. Okay? And I'm hoping that no one's asked. Let me escape from full screen just to make sure there haven't been any questions. So I'm not really sure if I can see any questions when I'm in full screen mode, but just unmute yourself and interrupt me rudely if there are questions. How about that? Okay, so let's go back to discussion of hadron masses. Okay, and again, you're all experts in looking at the effective mass from a correlator. And specifically, you read in the data. You got to figure out how to do if you aren't familiar with it. And this effective mass. And that's what I'm showing here. This plot way when I just stole from her slide, so you've seen this before. And you use the nucleon as a function of lattice time, and I'm covering up the numbers because again, we're not worrying about the numbers. And as you see, that you get this effective mass when you take this at large time, you get this nice plateau, right? And that's what you were looking for last week, or a little over last week. But really, the correlator has a general form of an infinite sum of exponentials. With these, this n runs over all states of the theory. And I wrote this as m bar and m, thinking I'm looking at mesons. But today we're really going to just look at baryons. Those are more fun because they're a little noisier. And of course, if you look at the effective mass plot, the fact that it doesn't plateau for early time is telling you that there are excited states in the theory, right? So if I sort of expand out this summation and I can look at the long time limit, then only the lowest energy states will be relevant. And again, looking at the effective mass plot, looking for a plateau is how you're looking for this first term, where generally speaking, E naught might be the rest mass of the state. Because usually, at least for what we're talking about today, all of our particles have zero momentum, and therefore the energy of the lowest state will, of course, be the rest mass. And again, these are ordered as would E1 we'll assume is going to be greater than E0 and so forth. The problem with fitting the correlate or fitting effective mass for a plateau is if you want to try to get these excited states, well, you can't really do that from the effective mass plot as easily. Also, you're throwing out information. You're throwing out this coefficient, this A naught squared, when you're looking at the effective mass, right? And there are actually uses for that, which we can discuss later if you're interested in. So let's actually focus on fitting the correlator. Okay, and how do we fit the correlator? Well, it's a nonlinear fit, right? Normally, and a lot of you may have had a class as an undergrad or in graduate school, or you've studied looking at linear fits, or let's be even more ridiculous. If you've ever used Excel in intro physics lab to fit a trend line, that's often a linear fit. Linear fits where the fit function, this y of x and alpha is my set of fit parameters, this is linear in all of the parameters. So fi of x could be any function. Okay, it could be an exponential, it could be a polynomial, it could be sine or cosine, but it only depends on x, not any of the fit parameters. And so that's what we mean when we say linear fits, that the alpha i's all appear linearly in this expression. But of course, with a nonlinear fit, right, if I have the effect or the correlator, which if I just look at the term, notice I'm changing my notation a little bit, but that's part of the fun. And I've got one linear parameter, the coefficient a, plus one nonlinear parameter, the mass, the m. And so this is a nonlinear fit. Now, notice that this won't be relevant for today, But if you had lighter mesons, for example, the pions or kaons, then you actually have to add in a second term, no new fit parameters, but this accounts for the periodic boundary conditions of the theory. Now for us, we're just going to look at this single term here. Okay, there are no periodicity issues for baryons. Okay, there is an interesting result from the other end of the lattice, when you wrap around the boundary for the baryon correlators. And if you notice something weird there and you want to ask about it, go for it. So how do we fit a function like this? Okay, well the procedure is basically the same. Okay, you want to minimize a chi-squared, right? That's really all fitting is. It's just minimizing chi-squared. And in this case, we'll start with the simple version of chi-squared, where we're going to take our correlators, which is a discrete set of data points, c sub I. So I is going to point to 0, 1, 2, 3 at the time, minus our fit function, which in this case is this function right here, a times e to the minus mt, okay? Square that, divide by the uncertainty in that data point, squared, and sum over all values. And of course, if we minimize this expression, then we'll say we have a best fit, right? Standard least squares fitting procedure. The difference is between a linear and a nonlinear fit is that with a linear fit, minimizing the chi-squared gives you a linear system of equations that you can just solve. Okay, so if you know how to invert a matrix, problems, trivial. For a nonlinear fit, however, you have to do a little bit more work. You have to do it iteratively. I can never say that word, and I think I was happy I just did it properly. And what you want to do, and a lot of what I'm doing right now, I just took out of numerical recipes because it has a really nice description of this algorithm. And one of the handouts I'm giving you is this section of that book, just because I think it honestly has the most concise, cleanest explanation. But we want to expand the chi-squared around its minimum in a quadratic form. Okay, and of course, this lowercase bold d is the first derivative of my chi-squared with respect to the alphas, evaluated at the minimum. And of course, that we would like to set to 0. And then this capital D is the second derivative of the chi-squared. And in this case, we will still need that as well in order to ensure that we're going down the hill, okay? And so if we want to do this, we can basically use something like the method of steepest descents, which you may have heard in some of your classes. Basically, we choose some set of parameters, alpha j, and then we update that by subtracting off the gradient of the chi-squared when evaluated at those parameters. Okay, that's going to allow you to go down the hill, right? The gradient always points down the hill. So we can see this graphically, and this is actually a chi-squared for one of the fits that you'd have to do today. You can see it's kind of a fun little expression or figure. Well, imagine I'm at this point here. This is my alpha j. Okay, I guess it's 0.05 or so, and I can't read the about 0.3 or something. Okay, obviously this point is not the minimum of the chi-squared. The minimum is somewhere down there. But what we would do is calculate the gradient, which will always point in the direction of the largest change. That's the glory of the gradient. And specifically, then we're going to multiply that by some constant. And that constant is what makes an algorithm for this. Okay, it changes from algorithm to algorithm. And that'll tell us how we change all of our parameters, these alpha j's, to get our updated value. Okay, and then we're going to just keep doing that. Now, so of course what we're going to need are the derivatives of the chi-squared, and so we can define these matrices of the derivatives, okay? This matrix A, so this J is going to run over the number of data points we have in our fits. The K and L will run over the number of parameters, and I've been very lax of putting down variables here just because keeping track of variable names is always a pain in the butt, isn't it? Now remember, this matrix A is the same matrix you would define in a linear fit, but the difference, as I said, is that these derivatives here, these partial derivatives, have likely a dependence on alpha still. So we have to be very careful in doing this procedure. We can define this beta, this vector beta. Again, J is running over the number of data points. And this is looking at sort of the difference between the C sub J's, or the data in the model, times the first derivative of the model with respect to the parameters. And now what Levenberg and Marquardt did, besides defining these particular versions of these matrices, is they scale the diagonal elements by fudge factor lambda. The value of the fudge factor doesn't do too much. Okay, so we're going to look at this matrix A prime. Okay, so all of the diagonal elements get scaled by lambda. All of the off diagonal elements don't change at all. And then we want to solve this equation, set of equations down here, okay, for the change in alpha, okay? And of course, we have some initial alpha. We calculate the change in alpha. We update the alpha. Lather, rinse, repeat. So there's the equation again at the upper right. And here's the basic algorithm, okay? First, you take a guess at what your parameters are. And notice this is where calculating the effective mass is helpful, because that can give you an idea of roughly where the mass should sit, right? So that'll give you a good guess of the initial parameters. And a lot of these fits can be highly dependent on your initial guess, okay? And of course, it depends on the particular data you're analyzing in this way, but so a really bad guess could mess up your results. And then you compute the chi-squared with your initial guess. Have a modest choice for lambda, let's say 10 to the minus 3, okay? Then you solve the equations above, right? For the change of the parameters, change the parameters, and then compute a new chi-squared. If the chi-squared increases, then we're going to want to keep running through the algorithm, but we want to increase lambda because we want to get down the hill. So you maybe multiply it by 10 or so. Again, the exact numbers here don't really matter. However, if the chi-squared decreases, then we either will stop if the chi-squared decreases by a small enough amount. Pick some stopping condition. It could be 10 to the minus 4, 10 to the minus 5, depending on your choice. Not going to be. You don't want it to be too small. You don't want this to run too long or to start doing random sampling. But if you haven't hit the stopping condition, decrease lambda, because you're going in the right direction. You don't want to make drastic changes anymore. And so you might divide by 10, okay? And then keep going until you hit some stopping condition. And again, you never stop if the chi-squared increases, okay? So, a little more details here. Once you get your final parameters, you've got this matrix A now, and the errors in those parameters would be given by looking at the inverse of that matrix. Specifically, the error in the ith parameter is the square root of the diagonal elements, okay? The off-diagonal elements will give you correlations between the parameters, okay? And so a good fitting routine will be able to evaluate those as well, okay? And if there are severe correlations between the parameters, then you may not want to actually just list off the uncertainties in each parameter. You may want to actually make a parameterized plot of, say, in this case, the fit parameter for the coefficient, which I'm calling A, which I realize is also the matrix that we're looking at, but such is life. And then one axis being the mass that you're fitting, and you might get some sort of ellipse for how the correlations go. Again, we're not going to worry about that too much with our mass fits here. Those aren't usually too significant an issue, at least not at the level we're working on right now. And the big question is, and this is really where the science of statistics become more of an art, or you may say black magic, how negative you want to be about it, how do you tell if a fit is good? Well, we like to say that the chi-squared per degree of freedom should be of order 1. The idea being, let's go back a bit, right? If we look at our chi-squared, right here, remember sigma is the error of our data points. And so generally speaking, our data should run roughly equally on either side of our fit function. And at most of order sigma. So this numerator in the chi-squared should be of order the denominator, and therefore this should be about 1. And so if I had 10 data points, then I'd sum over those 10 data points and get 10 from my chi-squared. But every fit parameter you add in restricts the fit a little bit. So you want to subtract out the number of parameters. And so the degrees of freedom are given by the number of data points minus the number of fit parameters you have. And of course, you don't want too many fit parameters. And you also don't want too few fit parameters. So if this ratio is roughly of order 1, then we're going to say the fit is good. If this is much larger than 1, then that probably means you've either underestimated your errors, which isn't a terrible thing, but that could be an issue, or you just have a bad fit function. Or, which is going to be important today, you'll notice you maybe have a bad data range. Remember, the effective mass only plateaus for a long time, so the early part of our correlators we don't want to fit, because those should not fit a single exponential very well. So if you choose too large of a range, then you're going to get a very bad fit. Okay. If the chi-squared per degree of freedom is too small, then you start to not really trust your errors. Maybe you overestimated your errors on your data points somehow. You can make the argument that you can always fit any function as long as your errors are large enough, right? And so there's a sort of balancing act. Now, there are better methods by which you can test the goodness of fit. Okay, there's the Q value or confidence level. There's the P value. There are all sorts of different variable names valued that you can use. And I encourage you to look some of them up to sort of see how you might be able to apply that to what we're doing today. But again, we're looking at sort of the first pass of just trying to get some decent results out of these the data that I'm going to share with you. Okay, and this will be a good enough way to look at it. The key is that if the chi-squared per degree of freedom for several different fits are around the same, okay, then you have to try to decide which one is better or which one is worse, and so forth and so forth. Okay. So here's what the rest of today is going to be, or at least the rest of this morning going into after lunch. Last week or a little over, you determined the effective mass. Hopefully you all did finish that exercise. Haha. And so now what I want you to do is you hopefully still have that correlator that Wei Wen shared with you. And I'm going to give you a bunch of others. Okay. And what I want you to do is fit it. Fit those correlators and extract these masses out from all the data sets that I have. You are welcome to code this algorithm from scratch. I don't recommend it. But you could try. I'll give you some working code that assumes that you've read in the data already. Okay. And I'll show it in a second actually, so that you can sort of see it. But the code that I'm going to give you actually uses the lmfit Python code from this site here. So you can download that. And you can easily, on your computer from the command line, do pip install lmfit to install this set of libraries. And you can go to this site in order to figure out how to understand what you're doing with these fits. Okay. You're also welcome to Google Levenberg-Marquardt algorithms for Python, or if you'd rather use C or C++, or if you're one of my friends here who hasn't left the 60s, use Fortran, whatever. Use any thing you want to do this, that's fine. But here are your goals. Okay, so I'll leave this up here in a second. And actually what I'll do is I'll send this link to you all through the chat window, both of these links. And this is a zip folder of a lot of the handouts that you're going to need for today, okay? This includes the data files that you're going to be fitting to. Note the weird name structure, so you have to deal with that. And basically, there's a whole slew of goals here. Get the masses with the uncertainties. Okay, include your chi-squared per degree of freedom. Okay, and then when you first do this, right, you're probably going to just sort of hard code a lot of things to make it just work and be able to read in things a certain way. But you may want to make it so that the code is more general. Okay, make it so you can use command line arguments or whatever. The big zip file is in a Jupyter notebook. And again, you can just copy that and paste it into a text editor and use Python or IPython if you'd rather not use Jupyter. But so try, making more general code. One interesting aspect would be to try to see if you can extract excited states. So I can, instead of having a single exponential fit, which is what you should start with, try adding in a second exponential where your fit range will change because, of course, the second exponential, this M2 should be a heavier mass, and so that'll be relevant for earlier time. Probably the most important thing is to modify the chi-squared in order to be able to fit correlated data. Okay, so you've already done jackknifing to take care of the correlations among the different configurations. Okay, but what about the correlations between different time points in our correlator? Right? If the t equals 2 point goes up a little bit, then it's likely that's going to affect the t equals 3 point. So all those different data points are correlated, and so you can calculate the correlation matrix this way. Remove that n-1 factor if you're using jackknife samples, okay? And find a way to modify the chi-squared in LMFit to use this different expression, okay? Also, if you want, if you have time, especially if a lot of this is easy for you, then you can go and look up the bootstrap algorithm. So go have fun. I always like to call this stuff fun. I've been told that too often by my students that when I say something is fun, that means it's going to be hard or miserable. But I don't really see the difference in the two. So what I'll do is I'll escape out of this. And I'll send copy. Oh, okay, well, I'll do that then. I'll copy this and I'll send this window. Okay. And then I'll also send you the link for LMFit you can download. And of course, I'll go ahead and stay logged in, obviously, to WebEx, and hopefully you all will too. And ask me questions as you're working on things. We'll hang out together. It'll be a good old time. Again, you can chat either directly to me or ask them out loud. I'm not entirely sure how you worked on these projects last time with Wei Wen, but if you want to work in groups, even though we're all spread out all over the place, you are, of course, welcome to do that. If you'd rather work by yourself, that's wonderful too. I'm not going to collect anything. Okay, I'm just going to let you do it, and we'll work on this for the next 45 minutes or so, break for lunch, or you keep working if you'd like. And then around 1:30, we'll come back to the new WebEx link and keep on working on it. If everyone finishes early, then we'll discuss. We'll spend probably the latter chunk of the second lecture discussing the results that you all get. But before I sort of stop blathering on, any questions from anyone? So silent.
No, I thought that was great, but yeah, I think a lot of people in here actually know Fortran now. I gave them a talk on it last week. So
Okay, cool.
Doesn't mean we're using it, Paul. We don't live in the 60s like you.
hey, C only came out in the 70s, so I mean it's kind of like
We're using Python. We're modern lads.
Yeah, exactly. I had my only real experience with Fortran was in when I did research in Oklahoma in '98, where I had to debug Fortran code, and that was enough. I was done after that. So yeah. But hey, if you want to use Fortran, go for it. That's awesome.
yeah, I think if your first exposure to a language is debugging someone else's code, then I think everyone will hate every language.
That is true. That is true.
I still use Fortran. I'm a millennial, so
Good. You can keep the tradition going. That's good.
But yeah, no, thank you. Yeah, we'll try this.
Right. Excellent. Oh, I'll do. Oops. This. And
Oh man, I'm really impressed someone knows COBOL in here. Oh, Dr. Geet, say I'm surprised the government hasn't hired you to rework the deployment system because they're looking for COBOL programmers.
Or the nuclear missile launch codes.
Or no, that was from Nicholas. Yeah.
yeah, I've actually only started learning Perl because I've been creating homeworks in WebAssign, which uses Perl for its homework or question creation system. Here, what I want to do, yeah. Let me also real quick, everything ready. I'm gonna, where is it? I'm gonna share my this Jupyter notebook that I shared with you. The just is essentially what we've already talked about. Notice this uses two lines here are importing from LM in the derivative section. Since you've already written data to calculate the effective mass, you can add here whatever reads in whatever you do to read in the correlators, and then of course down here is where the fit actually happens. Okay, and so you'll see the functions I use, which you can again look at the LM fit um, documentation, which is actually fairly good for documentation to understand what that does and how you can. It's actually kind of nice how smart it is. But be sure to pay attention to the way that it's going to expect you to have the data read into. So,
So,
and again, oh, go ahead.
sorry. We need to put in our own Jackknife data thing.
Exactly. Yeah. So
Okay.
basically, whatever you did before to read in the data under the Jackknife, basically replace this all here or put it somewhere above the mod equals line. So that should be pretty much done. The only key is making sure you read in the data files correctly, and then looking at the different files that I've given you.
And a question, when you say the jackknifed errors, what do you mean for that?
So when you read in if you have a set of Jackknife samples, let's say you had 100 data points or
Yeah.
100 configurations, then you've got 100 Jackknife samples,
Mm-hmm.
then standard error or the standard deviation of those averages are the error, the Jackknife error.
Is there
Okay.
only one error though?
For each time point will be, yes.
Oh, okay, okay,
Yeah.
okay.
Yeah.
Because the errors was throwing me off. I was like,
Oh yeah, yeah.
if you have a whole list, should it be one? Okay.
Right, right.
Should I also ask, which is the primary data file? Is it the DS store?
No, no, ignore the DS store file. That comes from just the details of I can't even think anymore of the Mac OS and Dropbox. So there's what you should see. Let me go to my data folder. Is all these delta underscore HG underscore blah blah blah. So you'll see
Yeah.
all these different, all of those are different ways to represent the delta baryon on the lattice.
Oh, so they're all different, like sims, or?
Yeah, yeah. So they're all run on the same configurations, but with different operators to create and destroy the delta. Same with the nuke. The four different nuke files are four different ways to create a nucleon. And so you can fit all of them. The nucleon fits should all give you consistent masses, and all the delta files should all give you consistent masses as well.
Okay.
And I gave you the full messy ass name just to so that it's complete in terms of the group theory and the source and sinks used. Uh, Also, I'll point out if anyone finishes all of this and would like to do something more interesting, as in fitting non-zero momentum deltas and nucleons, I can give you a whole bunch more files where you can actually calculate the dispersion relation, the energy as a function of momentum for these guys. So I've got plenty for you to do if you want. Um, and as many of you may have noticed already, if you look at the data files, they're in the same format of the data files that Way1 gave you because they're still using the same Chroma source code for Lattice QCD. So I don't want to confuse you that way too much.
Named LM Fit.
Yeah. So then be sure that you need to basically go to the GitHub page that I sent you and install the LM
Oh,
Fit
it's not
library.
default. Okay, gotcha.
It's not default, yeah.
I was gonna say on the link to the LMFit page, it also has like installation instructions using Conda or pip.
Yeah, so it has the instructions for Conda and pip. So if you use pip, that's the easiest and fastest way to do it. If you use Conda, obviously. Yeah. Again, it's a pretty good um, set of pages. Yeah.
What are like the differences between using pip versus conda? I guess obviously if you have the conda, or if you don't have the conda package, you can't conda install it. But is there any benefit to using one or the other?
I think
I,
Conda's
I, I
just
personally think it's personal preference. I think Conda, it's more all sort of in one big package, and it's got its own way to do file management and installation management. I ran into annoying issues with it a while back. I can't even remember what they were, so I switched to using, well, on a Mac, Homebrew, and then pip to install everything. Um, my guess is that anyone you talk to will have their own religious feelings about which is better and which is not.
yeah. I ran into an issue uh between Anaconda and the IDLE Python, and then just using the Ubuntu install, because all of them had their own Python installation, and it was getting confused with environmental variables, and none of them would run any code because they were looking at the wrong interpreter in the environmental variable. So having multiple installations of Python can really make your system confused.
Yeah, that is the. If there's any major downside to Python, it's that it's sort of all over the place. You can have all these different installations, and I have some students who are using Python on Windows using Cygwin, and it took them, and I don't know Windows very well because I use a Mac, so it took them several days to be able to get SciPy to install properly because for some reason the Cygwin installations they used for Python didn't want to work, and the NumPy installations didn't want to work properly. I don't really know what they did to fix the problem. All I know is that it started to work, and that often happens with Python. But yeah, I think I remember having some sort of similar issues with Conda, which is why I gave up on it.
How do you? So I just tried to install it through the Conda PowerShell, and it looked like it worked, and it's still giving me the no module LM fit. How do you?
Try.
What is pip? How do you do that?
You use pip from the command line. So
Which command? The Windows command line?
um,
Python?
it depends. So yeah, I'm not. If you're using Cygwin, then you can go into a Cygwin terminal and use pip. Usually,
Okay.
as long as it's installed, that's the way I've done it in the past. Again, as long as Python is installed there. I'm not. I don't know much about Conda. Maybe someone else in the
No, I
class
have
knows
no
knows about
preference. I
Conda to
just
help.
need to. I
Hey,
don't know what
hey
pip
Nick.
was. So.
Yeah, hey Nick. Are you using Anaconda?
Yeah.
Okay, so then what terminal did you?
The Anaconda PowerShell prompt.
Okay, that should have been. That's the right one. You need to restart your kernel in Jupyter Notebook.
I did. I completely shut it down.
Okay. Alright, that's all the help I can give. Okay.
God damn it.
Did you do all the dependencies? Like when I Conda installed it, it was like Conda Forge something.
It only wanted Pillow, but I already had it installed.
So the command I ran exactly was Conda install -c Conda Forge lmfit, and that worked.
Wait,
I,
can you read that out again?
here, I'll paste it in the chat, but I literally just looked it up on.
Okay, I used the GSecHars one that they recommended. Let me try this one.
Here, I tried this one.
This is the glory of programming and computational physics. Everyone has their own expertise. Stuff I do not know about.
Mine is few and far between, thankfully. Other people know what the hell they're doing.
Yeah.
Did that work?
It downloaded pretty fast, so I don't know. Let's see.
It's also so much easier now to program with Google. Back in the 90s, it was a little more difficult. You kids these days have it so easy.
Yeah, it was really hard for me to compile code when I couldn't read back in the 90s.
When you couldn't read. Nah, it's still giving me no module LM fit.
Really? What?
And I restarted it and everything. Actually, no, I didn't restart it. Let us pray, brethren. I have a question. What's your preferred method of navigating folders? So the change directory to data worked, but then when you try and run it again, I guess it saves your directory. Is there a preferred way? Because I know like a lot of people like to use like with f as file.open or things like that that seem to do it better.
I mean, I'm not sure if it's the best way, but what I tend to do is I create a directory name as a string that I then put when I'm opening the file. If I do f.open file name, I'll include the entire path in the file name.
I see.
And sometimes what I'll do is I'll give the directory itself its own name, so the file name has a separate name. So I'll have like maybe direct equals data, and then do like f.open, oops, direct plus file name or something, comma r, something like that.
Gotcha.
Just working away and everyone muted is driving me slightly crazy. That's okay.
could unmute myself so you can hear me swear whenever it doesn't run.
Coding frustrations are best suppressed.
No, I think they're best outwardly shared. That's a good thing.
I mean, usually it's just me forgetting like a parenthesis or something, so there's not a lot for me to really ask about at this point. I'm still trying to get through some of these.
Yeah. The difficulty with the online version of this is that obviously in a regular situation, I would just be walking around staring at you all, making you feel nervous and self-conscious, but I can't really do that when I don't see your videos and I can't walk around. It's rather unfortunate. Although Anthony knows what I'm talking about. He had to deal with that before, so. You're still kind of wait. We sort of get results of some sort. Let's say you've fit some of the data files or a data file, and you realize that you think that the mass you got for a given data file. You trust your fit, and you think it's a good fit or whatever. Shoot me a message. You can either do it publicly or just a private message on chat, or you can also, if you put it all into a nice LaTeX document, which would be preferred. If you know LaTeX, then you can just email it to me what you got, and I just sent you my email in the chat window. That way, if I see if I see the majority of you have gotten, a certain part of these goals finished, then maybe after a little while, I'll stop you from working on all that, and we'll have a little discussion. But yeah, for the most part, it's going to be just continuing what we finished from the latter half of the first lecture. So be sure to ask questions if you have any, of course.
Yeah, I have a quick question.
Yeah.
I think I deleted my X on accident, and I can't remember what it was. Like,
Oh yeah, my code was having a problem with the X too. I don't know if it was defined or if we were supposed to define it.
I think I might have like accidentally erased it, but
so like this X right here.
Yeah.
Down further in DOF, it doesn't know like
Or it was right above.
I think it's also that's a change in what I had originally done for this. This should say times.
Oh.
Yeah, so that was there. That was my fault. I tried to change this a little bit to make it a little bit more readable. So times, this will be, notice that times here is the minimum to the maximum time range. So that'll be the number of data points you're going to use to fit. So that's what this should tell you. Yeah, so it shouldn't have said, originally I actually had this even say x equals that, which tells me. So I changed it to times, but again, like I forgot to change this part down here. I forgot to change that to times. So that's probably that problem coming up.
What was the second fix after the DOF was changed?
I was just saying that was the X. That was where that X showed up.
Okay.
Yeah. So here, the LM Fit modules or code uses X for the independent variable. So notice that's why in the model, X here is what we're calling time. And so this is just saying that the X values, the independent variables, are going to be those that are in the time array.
Okay.
Okay, now it says it doesn't know what core is, COR.
Yeah, that was another issue I was having.
Yeah, so look at the new PLT error bar line that I just highlighted. That's the problem. So
okay.
It should be this guy.
CERR. Okay.
Yeah.
With a capital. Yeah, with a capital.
Yeah.
Okay.
So is anyone else? So someone's asked. Travis is asking. Is anyone else is getting nans using NT over 2 as T max? One quick question: Are you capitalizing the N in NT? Because at least the way I have it, it's lowercase, but that. Okay. Huh.
I'm still getting x is not defined, even though I have x equals time. You might have to manually set it.
I just set x is equal to times.
Okay, yeah, I thought it might automatically do that in the out statement if it uses x equals times, but
Oh, I see. Oh. But now mine says that there's too many indices for array right where I plot it, the x versus c average. So x has to
Oh,
be the same
yeah.
size as c av.
So then down here under plot error bar, that should also say times. Unless up here you said x equals times.
yeah.
Yeah, that's what I did.
Um,
But
You're getting an array size mismatch?
yeah.
So what I did is you might have done this, I'm not sure, is my issue was that I was trying to fix the code myself by making x the time things, but it's arbitrarily started like at step 12, so I got array mismatches. So maybe if your variables weren't cleared, I'm not 100% sure, but maybe a kernel restart would tell you if that would be it. I'm not sure if that would be it, but
yeah,
I also just
that was
set.
an issue that I was having that I couldn't figure out, and I finally figured it out.
Okay, I think I should just get rid of x to begin with and just do times. I think that's the quick fix, maybe.
you can email me or post the masses in chat. That's fine. If you're gonna send them to me in chat, send it to me privately just to not give anyone else the answers. I'm trying to understand Travis's question. So the model function generating NaND values in the fit of board. Let's see. Please check your model function and or set boundaries. Okay. All right. Oh, weird. That's very strange. Yeah. So also, Travis, did you have so did you make the changes, Travis, that we were just talking about in terms of changing times? And yeah, that is an interesting. And you did not change the expression model. It's just using exactly what we have here. Okay, that is interesting. This is an error that I don't understand. And so Travis also, did you get here actually maybe let's see. I might ask you to share your screen a second. Are you getting fit parameter values or just or nans everywhere? Or so it just did not complete? And then while I wait for okay, so let me answer a couple other questions by chat. All right, so we got a question about, and this is always good to, I'll answer this publicly. Got a question, what is meant by reading the correlator data under a jackknife? Okay, so you're familiar with jackknife resampling. And so what'll happen is when you've got your, in this case, 331 jackknife samples, you'll run the averages for each time value. And then you should get a one-dimensional array with, in this case, 128 elements. And those would be your average values for C of 0, C of 1, C of 2, all the way down. Then you take those 331 samples and calculate the standard deviation of those numbers for each time value individually. And then that will be the jackknife error. So that's what I mean by reading the correlator data under jackknife. So CAVG will be the one-dimensional array with the averages over those jackknife samples for each time value. and then C error will be a one-dimensional array of the same length where it has the standard deviation of your Jackknife samples. And so hopefully that answers that question. And let's see. Okay. All right, let's see here. All right. Let's see here. Okay, yeah, so just a reminder, the numbers at the top of each data file. The first one, basically you only really need the first two. The first number on the top of the data file is 331. That's the number of configurations. NT is the second number, 128. So and I'm just reading lots of chat responses here. This is nice. I'm not just laughing at my own face. Also, when you do send me your mass, tell me if you're looking at the nuke NUC files or the delta files, because that'll change the numbers, and that'll change how I can check. Oh yeah, and just FYI, in the output for the fits, when it says reduced chi-squared, that's the chi-squared per degree of freedom. So okay. Okay. Yeah, so for the 4 nuke NUC blah 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 files, you should get roughly the same. You should get masses that agree. Okay. Um, some may or may not be more or less noisy, and then the deltas, all those files should have the same value. And so you should get 8 delta masses and 4 nucleon masses. That should be So there are several questions, both publicly and privately, about the chi-squared per degree of freedom, or the reduced chi-squared, and the fact that you're getting very small values. And that is something we're going to talk about later. Okay. Because yes, I did say that it should be close to 1, but there are some caveats with that that statement. So for now, just sort of record what you're getting and see how it's working. And then we'll discuss more maybe near the end of the lecture exactly why that might look different than you would normally expect. Also note, I'm not gonna say if your results are correct or not. Okay, just because it's more fun for you to try to figure out yourself. One of the things you want to look at is see what happens when you change the fit range for the time values. The Of course, if you go to lower time values, some of you have already pointed out that that you'll start getting much different masses because you'll get contamination from excited states. And as you increase the minimum time point, then you should see a stabilization of the mass fits for each data file. One thing you can do in order to check, or one thing you can do is make sure that you're outputting pretty plots, right, with labeled axes and things like that. You can also start looking at adding in a second fit function, right? Up here I suggest using this fit function here, this double exponential fit, and see how that changes things. If everything is working well, you should get the same expression for the lighter mass. And most interestingly, and probably most importantly, would be to see what happens when you, try to modify everything in order to do a correlated fit. That's going to be a little bit more work with the LM-fit module.
Complete noob comp sci question. If you want to skip the name of a file in a loop, it's like I'm looping over the files in the data folder, and I want to skip the DS store file because it's gibberish. Right now I have if the name is DS store, break the loop. And is that the proper syntax to skip over a file name?
Well, if it breaks, if that may not allow you to read everything if it ends up being the first one read in. I mean, one way you could do it is just delete the DSTOR file since it's worthless. You could also make sure that you're looking over files that have only the proper naming. Maybe you'll look if the first few like the first three characters of the string of the file name are DEL or NUC, you'll add it, otherwise skip it.
Mhm.
That might be a better way to do it.
Say, Nick, in an alternative way, instead of using break, use continue.
The issue is, I think I don't know how to set the equality. I'm trying to say, like, if the file name is this, then, don't do it.
Oh, it's a double equal sign.
No, I
Right.
have that. It's if the file name equals quote dot ds underscore store, and I don't think it likes that.
We could do if file name and then say the first three characters equals, and then put, dot ds. And that way it'll only read the first three characters of the string. That could work. That would work, or should work. Is that working?
I think the issue is with the naming scheme. It isn't triggering the if statement, even though when I ask it, oh wait, maybe I think I probably need to typecast it as a string.
Yeah. Are you talking about the file name or the pointer when you've opened the file?
I think it's hitting the pointer right now, which is the issue.
Yeah. So before you even open the file, you should, like, before you have the f dot open blah blah blah, whatever you're putting into the open should be checked to see if that has the name that you want.
Gotcha. Okay, yeah, I figured out the attributes in the thing. You have to do, object dot name parentheses, and that will give you the actual name of the file.
Okay. So once you've opened it, it'll do that.
Yeah. So I was using the entire object, which I
Yeah.
assumed was a string, but it's an object with an attribute name.
Right. Okay. And see, this is why it's so much better for you all to be doing this sort of stuff instead of me blathering on for another hour and a half. I learned so much more by going through this painstaking process.
Yeah.
So also just because I got a couple of questions here in the chat. Um, one thing, obviously you don't want to. This is part of the generalizing the code comment that I have in the goals section. Make it more general, where like some of you are running a loop through the the directory the data files are in to get all of the data. You can put in loops to do fits over all sorts of different time ranges. And you could also write out the results that you're getting to a file, so that once you do a fit, you'll save the file and save the results that you can then look at later. Um, all of this is sort of part of the figuring out how to make this little dinky bit of a piece of code be more useful for broader applications. So below this, you could even not you could doing the plt.show, you might want to just save the figure to a file named based on the file name that you read in, and then create an output file that you can then output these fit results, the fit report, for example, in order to then have a whole slew of results in your directory that you can then later look at. That's also part of how you get to make this more how you want it to work instead of how I would tell you how to do it. Oh yeah, and also just as this was a question that popped up just now, if you do start adding in the second exponential, you'll definitely lower T min, because the larger the T min, then if you have a very large minimum T value, then you're only going to see the ground state, that lowest mass. And so if you add in an additional exponential, you're going to basically just be adding noise to the fits. So in order to try to get that be able to discern that higher mass state, you'll definitely want to decrease T min to see something interesting. And Okay. Oh, okay. Right. Okay. Okay. Also, a couple comments while you're all just working away. The easy stuff to change the code of the first, 3 or 4 goals. The 2 exponential fit, adding that is fairly straightforward. General read in, like some talked about, multiple files and things like that. Those are all sort of the more straightforward things. Um, the harder part of with using LM fit is the fitting to correlated data using that correlation matrix that I described here. Um, you can create that correlation matrix when you read in the data, and that's a little bit of a hassle. But once you do that, then you also have to change exactly how the chi-squared works. And so you'll need to dig into the LM fit code a little bit more than just looking at this fit function, because this fit function uses the standard uncorrelated chi-squared. That's what the weights are coming in as. So you have to dig a little bit deeper into the documentation of LMFit to do that correlated fit. So that's a little bit more involved, but of course it's also a very useful thing to know how to do. So that's why it'd be a good next step.
Are there any special considerations when we're adding the extra parameters? Because I added the what looked like the initial guesses, and I changed the guess model, and it worked for the first one fine. But then when it went to the second file, it's throwing some errors.
What kind of errors are you getting?
It's not like a short error. It's the model function generated NaN values and the fit aborted.
Oh,
Is
yeah,
that like
so
convergence issues?
yeah, try making sure that the initial guesses are different.
Okay.
Do you have the same values for the initial guesses?
Yeah, I just use the same ones, and I'd imagine.
Yeah. So generally, what you would expect would be the like A1 and M1 would
Probably increase the mass of
yeah
the
increase
second.
mass, decrease the coefficient. Yeah, that's
Okay.
what we would normally expect.
I resolved what it probably was. Almost the instant it came out of my mouth, I realized I hadn't tried that yet. Yeah, that worked fine. Thanks.
No problem. That's why you also need a little stuffed animal to talk to while you're deep. You laugh, but I had when I was in graduate school, I had a stuffed Chihuahua, the Taco Bell Chihuahua, on my desk that I would sit there and read my code off to.
That sounds like a fantastic idea, except my roommates might think I'm a serial killer. But
That
it'd be worth it.
doesn't matter. Hey, it'll make them be careful around you.
Yeah, no. I used to use my roommate as that sort of rubber duck for troubleshooting my code, even though he had no idea what it was. He would come in and like look at it, and he'd be like, "Well, have you tried doing this?" And I'd be like, "No, that's not it." And I'd be like, "Because of this and this," and I'd be like, "Oh wait, that's
It,
the problem." Okay.
it's a story as old as time.
Exactly. It's the beauty and the beast. I guess no one got the reference of the tail is.
Why was it again that we had to remove the n-1 from it?
Because when you do the Jackknife sample, the error in the data points is coming from the standard deviation, not the standard error. And so the difference between the standard deviation and the standard error is divided by n-1. And so you put that back in.
Oh, I see. Okay. So when you loop over that Jackknife, you leave that off, right?
Yeah,
Okay.
exactly. Or sometimes I have had some versions of the code where I put it back in because I use built-in standard deviation functions and things like that, or standard error functions.
Okay.
But hopefully I got all the questions so far.
And then maybe I'm jumping ahead, but for bootstrapping, it's the same as Jackknife. You just randomly pull one out. Is that my understanding of it?
Well, it's sort of backward. It's you're doing it differently in a weird way. So with Bootstrap, what you're going to do is let's say you've got, I'll just say 100 configurations instead of 331. Then you decide how big you want your Bootstrap sample to be. It could be the same as 100 as the number of configurations, but it could also be any number. You could say 50. Then you randomly select 50 configurations from your set of 100, and they could duplicate. You don't have to. You don't require to select 50 distinct configurations.
Okay.
Then you do your average on that, and that's your first bootstrap sample, and then you do that 50, 100, 1,000 times, things like that. And you'll create a histogram, much like you did with Weiwen, um, of your results over all these different bootstrap samples. It tends to take a lot longer than Jackknife, and in many cases, the correlated errors are generally the same as the Jackknife, which is why a lot of people tend to just default to Jackknife.
Okay, gotcha.
And generally, one thing to keep in mind with all of these is, and I've said it before, and I'll probably always say it again. Um, a lot of the, statistical analysis is not really a science, right? It's more of an art. It's more of a black magic, where we're sort of doing our best to estimate everything. I never say. A lot of times we say we're calculating the errors or calculating the uncertainties, but to be honest, we're estimating them. And all of these different methods are different ways to estimate the correlations, estimate the effect of the correlations, estimate the uncertainties in your results. And one method is not necessarily better than another, but some may be more appropriate for different situations. And so you may never use. I mean, I don't use the bootstrap method too often, just because I can get a fairly good estimate on what I tend to do with the Jackknife, but that doesn't mean it's not important, especially if you are going to look at someone else's results and see how they're doing it. And always take with a grain of salt how good you think someone's uh, statistical analysis is, because quite likely fairly flawed, but they all are. So it's part of the fun. Oh, yeah, so I just got a question about modifying the chi-squared. So let me be clear. So on this expression that I have for the correlation matrix, this I is actually referring to the time value. So this is looking at correlations in time. So you've got this correlator that's a function of time. And so this C bar sub I is the average over the Jackknife sample for the time value indicated by I. And then same with the J guy. The K is running over the N configuration. So those N, 331 in this case, Jackknife samples. And so this is the correlator at time I for the configuration at K. And again, if those are your Jackknife versions, there's no N-1 out front. If they are not the Jackknife version, you do have the N-1. So let me um, I'll modify this as well. All right. So yeah, so we have about 20 minutes left, and while you're still working on things, let me just sort of mention one other sometimes confusing thing, if you ask me. And who knows, maybe it's not confusing to you, and that's good. But it always sort of tripped me up a little bit. There are two kinds of correlations we talk about with lattice data. One is the correlations that come into play among the different configurations, and that is a result of imperfect data taking. That is the result of generating a configuration from a prior configuration, so there's statistical correlations among those data points. that's what the jackknifing is taking care of, or hopefully taking care of, or if you bootstrap, the bootstrap would take care of that. Then once you get these error bars for each value of C of t, for each time value, then there's also the fact that the error or the value of, say, C of 4, that t equals 4, that value may, if that went up or down based upon its error bars, the way we're doing the fits now, that would have no effect on C of 5 or C of 6. However, that's kind of absurd, right? Because obviously, since this is an exponential decay, if a certain time value of C of t changes, that should affect the next point somehow. So there is going to be some sort of correlation among the different time points. And so when I say modify the chi-squared to fit correlated data, using this expression here, we're looking at the correlations among the different values of C of t over the jackknife, not among the different configurations. Okay, so in a sense, there's as I said, two levels of correlations that come into play here. In principle, if we did our simulations completely differently, let's say we generated each configuration completely statistically independently, then we wouldn't have the need for doing the jackknife resampling because there wouldn't be any correlations among those different configurations. However, we would still have a correlation among time points because this is a more theoretical correlation among just how the function is going to behave as a function of time. And if you start out higher, that's going to affect later on values of time. So I modified my version of the LM Fit notebook to include this sort of note here. Actually, this bugs me.
Could you repeat? You said there was a one-line statement you said that I feel like was really important, and of course I spaced out at that one sentence. You said jackknifing takes care of which correlation? Which one?
Right. Yeah. No, that's an important one. Yeah, that was actually the most important sentence of the day. No, jackknifing takes care of the statistical correlations among the different configurations. So those 331 configurations we're running in or using.
Okay.
This correlation matrix that is in blue here is taken into correlations in time.
Gotcha. In between the individual steps on the graph.
Exactly.
Okay.
Exactly. So maybe in order to have a little bit of interaction here, and of course, I don't like calling on people. I would never do that. But maybe everyone could pause for a little bit wherever you've finished working on this assignment. And let's have a little chat, maybe a Q&A or just sort of comments that you have based upon what you've done during this period of time. I guess I'll start by sort of saying it seems like several of you definitely, got some fits that you seem like you sort of trust, and you got you started working on the double exponential fits. Does anyone have any? First of all, does anyone have any questions about what they've done thus far, conceptual or physics based or whatever? And it could be anything, right? Because you don't even really know what data you're looking at. I just sort of gave you some blind data. Um,
So you're not limited to just these two states though, right? I mean, you can go like A3, A4 if you wanted to, right?
Yeah, in principle you can, and because the actual correlation function you're calculating has an infinite number of these states, and as you know, you'll see that already putting in a second exponential makes the fit a little bit more unstable. And then if you add in a third or fourth, it'll start getting noisier and noisier. Did anyone get a reasonable value for M2? And I'm not even going to describe what reasonable is. I'm going to see if you think you might have.
Yeah, I got. Let me scroll down. Oh no, hold on. I think it was in the neighborhood of 0.45, but let me check
I
again.
got 0.01.
Ooh, that's a good one.
0.01 for
Oh,
the
thanks.
excited state.
For M2, yeah.
What'd you get for the ground state mass?
Also 0.01.
Interesting. So, so you're somehow getting identical masses, which means that something went kind of wrong with the fit.
Yeah, I have
Um,
extremely big errors too. Like they're really big.
yeah. So, what was the fit range you chose to get those numbers?
Just the one that we started with from the first example.
Right. So for when you throw in a second exponential, you'll want to decrease the minimum time. Because that second exponential is going to die off pretty quickly because of the heavier mass. And
Oh,
so,
okay. So start higher than 12.
or
Go.
lower than 12, like
Okay.
6, 7, ooh, 6,
Okay,
7
yeah.
or something like that.
6.
I reran the code. I got ground state mass of about 0.27 and excited state of 0.52, running from step 4 to step 64.
Okay. And so, and then what are the errors on that 0.5 mass?
0.5 mass was plus minus 0.01.
Yeah, so not terrible.
That's what I got.
Well, look at that.
Oh,
We
thank the
we have
Lord, dude. I
agreement
heard
among people.
0.01 and that's good. And I was like, I'm done. I'm toast.
Yeah, and so there's also another question. I'll answer Benjamin's question in a sec. There's an entire group at Jefferson Lab that is devoted to such excited state fits. And one thing you can look into if this sort of thing interests you is trying to find ways to improve these higher exponential fits. Um, if you look into the Hadron Spectrum Collaboration papers, or look up generalized eigenvalue problems from online. So basically, generalized eigenvalue problem, and then just lattice QCD. And this shows a way to create a matrix of correlators that you can then diagonalize using a generalized value problem to get these higher states much more precisely, which is really relevant to understand the full spectrum of QCD. Now let me answer Benjamin's question about, so this is analysis on lattice simulation data. So none of this is, so this is data that was taken, it's old, probably around 2009, 2010. And we use this data to analyze. This is part of the data we use to analyze the magnetic moment of the delta and the magnetic moment of the nucleon data that I showed at the beginning of my first lecture. So there is quote unquote a right answer because there is a published answer for these data files. And so the masses you're getting, note, are in lattice units because we don't put dimensionful numbers in the simulation. So that's why these time values are integers, because those are time values in units of the lattice spacing. And therefore, the mass that you extract is actually a dimensionless number. And in order to determine what that number is in physical units, you would have to determine what the lattice spacing is. And that is actually also kind of a non-trivial task that I'm not sure if previous Lattice speakers talked about, but it's an important aspect of the entire problem or any problem in Lattice QCD. Um, let's see. Let me ask if there are any other thoughts. I think did anyone get a chance to actually put in a correlated data fit, or has anyone, or is that still sort of the task for tonight? Because of course you're going to be so obsessed with this, you're not going to sleep tonight. Okay, let's see. Here's a modified use. Okay. Oh, okay. So Adam says he's got. Okay, so massive point M1 of 0.3, and then what? So Adam, what was your error on math 1? Okay. And your chi-squared per degree of freedom? Oh wow, it got for correlated fit, it got smaller. So that's interesting. We'll have to look over that later. Because normally the I'll sort of finish. We have only a few minutes left, but let me finish with sort of a comment about the chi-squared per degree of freedom representing a goodness of fit. The difficulty with saying that chi-squared per degree of freedom should be around 1 for an uncorrelated fit, which is what the base fit you've been doing here is that it is not adequately representing the correlations among the data points. And so what you often find for an uncorrelated fit is a very small chi-squared, which a lot of you saw, 10 to the negative 77, 10 to the negative 30, things like that. Because you are artificially throwing out correlations that we know are there, this sigma matrix that we have here should be there. Can't use the same interpretation of understanding how the chi-squared should be on the order of number of degrees of freedom. And so it's actually, you can still use the chi-squared to say, okay, that's a smaller chi-squared than this was, so it's a better fit, but it doesn't have the same statistical weight, no pun intended, as if you had, hold on, okay, as if you had a correlated chi-squared. And so always be wary if you look at uncorrelated fits and the goodness of fit using the chi-squared per degree of freedom. It's a useful tool, but it is not by any means the only tool that should be used. Okay, and it's an easy one to throw out there because it's easy to just look at it. It's automatically calculated, but you will see. So you'll see. Actually, in this LM fit, it shows several other criteria or outputs when you run it. Right? There's the it shows the Ikaki criterion and then a Bayesian criterion for testing your fit. And you should look those up and research those because those are really good. Those are really good methods of testing how good a fit is, whether or not it is correlated or uncorrelated. And there really is not here, especially with data analysis, because there's so much, and a lot of times this is an entire semester or two of a statistics course. So what do I mean by an uncorrelated fit? An uncorrelated fit is just using the error bars by themselves on each value of C of t, which is what is done down here. This weights each data point by the error. So of course, the larger the error of a data point, then the less that's going to contribute to the chi-squared, which is nice because that way we know that we're going to use all of the data, but we're not going to trust the data that has a very large error. that's uncorrelated because you're only looking at the error on that one data point. However, if you have two data points, they're, especially in cases like this, they may be correlated, right? Because if this is an exponential fit, actually, I'll try to do it from your point of view, then I'll just do it this way, whatever. As if this is my initial data point or time point, and this is a later time point, if this goes up, it's likely this will go up as well. So those two data points are correlated. To take that into account, that's what this blue matrix is for. If you modify the chi-squared from what I showed in my slides to include this instead of just 1 over sigma I squared, then you're now going to add those different correlations to change the chi-squared. And yeah, usually that means that the chi-squared will generally get larger. And so this notion that the chi-squared per degree of freedom should be of order 1 actually has more statistical heft. Okay. And so yeah, so these are things that you can definitely research, and it's very easy to have gotten things incorrect. So, I do hope that everyone, learns something from all of this stuff, and hopefully, if you haven't finished all of these little goals that I've given you, you may decide to work on them later. There's a good chance that any kind of analysis you're going to do later, be it numerical or experimental or what have you, will involve a lot of these tools. And so even if you don't have to do it much yourself in the future, it'll be good to know all this stuff, because then when other people talk about these things, you can sound very smart by saying, well, I've done a Jackknife resampling of blah, 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 which was much different than my Bootstrap resampling, blah, blah, blah. And so, any other last minute questions before I guess we take a little bit of a break and meet back up in 15 minutes? Okay, I'm going to take from the silence that either you're all asleep. That's actually what I hate about everyone's video being off. It's better for bandwidth purposes, but you're all probably just asleep as far as I know. During my spring semester classes, there were several times I had to kick students out of the room because they clearly fell asleep or left their computer. Anyway.
Adam is safe behind the shield.
Yeah. All right, so I guess we'll take. Oh, go ahead.
Oh no, I was just gonna say, I for one, I unplug my mic while all this is going on so I can like, because I have headphones on, so otherwise it's like, it just feels weird.
I think you're muted.
Oh, someone muted me. Did someone mute me? Oh, that's okay. Maybe I didn't touch my keyboard, but who knows? Anyway. All right. Well, I guess we'll meet back up here in 15 minutes.
All right, great. Sounds like a plan.
Sounds
All right.
good.
Great. See ya. All right. Well.
All right, great. I just started the recording, so go ahead.
Okay, cool. Oh, there we go. So in the chat window, you'll see a Dropbox link to download these slides as well for later. So yeah, let's go ahead and get started. Again, I can't just for this case. If you do have a question, I don't know if I'll see a notification from the chat window. So just interrupt me during these lectures if you have a question. So as I said before, today's lecture, today's third lecture slot anyways, about what to do next beyond fitting the raw lattice data. You thought you were done, right? You got these nice masses, and perhaps you had a whole bunch more data files with different input quark masses, that you have all these different numbers that you've gotten, but now what do you do with that? So I could retitle this talk, just because you've finished the simulation and you've analyzed the data initially, you're not done. Okay. So we have to keep on trucking here. So one thing to keep in mind when we're talking about lattice simulations is there are usually three systematics that are very important. Okay. Um, the first two are the obvious ones. We are working on a lattice where we've taken continuous space-time and we've discretized it. So there's a finite distance a between each point. Should have put a grid back on here again. Did not. So finite spacing, that's often the most obvious systematic error that arises when doing the simulation. Additionally, we've taken our infinite space-time, at least as far as we know, it's infinite, and we've put it into a finite box. Okay, so we have these finite volume effects, which I'm labeling as finite L, where L will be the length in the spatial directions. We don't tend to worry too much about the finite length in time, but that's a different story. We can discuss that later if you wish. But one thing that is not always obvious is that there's also an issue with the input quark mass. So of the various parameters that come into play, one of the most important set of parameters are the masses of the underlying quarks, the up, down, strange, charm, and bottom. The top quark is too heavy. We tend not to include that into our lattice simulations. It has no effect. But either way, we've got to put those in. And up until recently, we couldn't simulate at physical values of the up and down or even strange quark masses. And so that's a problem because, well, we want to be able to use physical values of all of our parameters, right? So the data that you've just been analyzing was all generated at a finite lattice spacing. If I recall correctly, the lattice spacing was about 0.12 Fermi. Finite volume, I think L for those ensembles, again, it's been about a decade, so I would guess it's around 3 Fermi on a side. So that's not 3 Fermi is nowhere near infinity, right? And unphysical quark mass. And I think the quark masses for those would correspond to a pion mass of around 300 or 400 MeV. So the pion mass was notably. So now, of course, the data you had also was only generated at one quark mass and one lattice spacing and one volume. So that's another story. So what do we do? How do we analyze the data when we have all of these obvious systematic errors that have come into play? So I'm going to look at, again, some old data. This is even older than what I've given you to discuss some of the issues, okay? Because, again, we can't just look at the data and come up with a way to fit it. Okay, there's sort of a gut reaction we would have that if it looks like a line, fit it to a line, and that's a good starting point. So this is very old data from 2004 for the pion decay constant generated by the Milk collaboration. And the pion decay constant actually is a very important parameter in QCD, and it is calculated by using the coefficient in front of the exponential of the correlator for the pion. Now, you weren't looking at the pion correlators, but that's why we would like to extract that coefficient, is because it actually has use for parameters like this. Now, what you're looking at here are two different figures of this data. Forget exactly what the axes say, okay? What matters is the horizontal axis is basically the quark masses, and the vertical axis is the decay constant. These are in dimensionless units in terms of what's called R1, but again, you don't need to worry about that. Again, the data points are shown. There are squares and diamonds. The squares are at a finer lattice spacing. I think these are at 0.09 Fermi. The diamonds are at a 0.12 Fermi lattice spacing. And all of these data are taken at unphysical quark masses. And again, these are in weird units, so it's hard to denote exactly where it is. The physical value is somewhere around this point here, where these lines end. What I want to point out is, so this was all generated using, each of these data points was generated in the same way that you did these fits to those correlators I gave you. Imagine taking the coefficient A from those fits, or A1, and doing something with it, and you'd get each of these data points. So your data might have corresponded to, say, this point right here, for example. Again, completely different data set, but it's just an analogy. Well, now we generated that for a bunch of different values, and the question is, since these are two different lattice spacings, finite lattice spacings, at a finite volume and unphysical quark mass, how do we extrapolate? Now, your first glance is you look and, these 4 points look like they might fit to a line, okay? And you could do that, but that would not get you very far. I'll describe what is used in order to get these fits in a second, but the old way of looking at these fits doesn't incorporate the fact that we have this finite lattice spacing. Okay, and so there's sort of a problem with these fits, and you can see that in this number right here, the CL equals 10 to the negative 250. Now this is often goes by the name Q value or confidence level. This tells me the farther this is away from 1, this can range from 0 to 1, the worse the fit. So we want this ideally to be 1. 10 to the negative 250 is rather small, fairly far from 1. And so there's a problem. And for a while it was thought, okay, there's something really wrong with how we theoretically understand the data. But then if you go to understanding something that we'll discuss shortly and add in the proper finite lattice spacing and finite volume effect corrections, you get the fit on the right, okay? And notice the confidence, ignore the second number, the confidence level is this 0.65. Okay, not, it's so, 65% confident that this is good. What matters is it's a much better fit, okay? And so if we don't have the proper theoretical background to understand what we're analyzing, then we can't get a good fit, okay? So that's an important aspect when going from one to another, okay? And then notice that what's nice is the formalism we're actually going to discuss today is used for all of this, for the finite lattice spacing, the finite volume, and the unphysical quark mass. And that's what gets us to this number down here. Now, these are very old results. They are far more improved nowadays by many different collaborations. But again, this is what I don't know the most about, and I kind of like it. Another aspect, and this slide is the slide is completely empty of text because I'm going to discuss this exactly these plots in much more detail later when we talk about the anomalous magnetic moment of a muon, which I touched on during the beginning of the first lecture. What we're seeing here is this figure, and notice the axis outgold. Horizontal axis is momentum, well, momentum squared technically, and what you see data points. These red points are data points from a lattice simulation of this quantity. I'll describe how that goes about later. And it's actually scaled by a function that's relevant for this calculation. What matters here is that in order to actually extract this muon g minus 2, we need to actually integrate over these points. But notice the points are very discrete because of the finite volume. You have this discretized momentum when you have a finite volume. And so the problem is you can't get any lower than this value here. And the real problem is that if you try to, let's say you do a fit, right, to create a smooth function, right, you can see that the peak of the function is to the left of this data point. The majority of the integral, or of the value for this minus 2, which again will be more clear later, excuse me, is below where we can even extract any data. So there's a big problem, which we'll discuss later, when trying to understand the fits that you'd get from this result. On this side, and again, I'll discuss this plot in more detail, these blue points are the original lattice data points. And these other three colors are different corrections because of improper mass tunings and finite volume effects and finite lattice spacing effects. And you can see, especially for this larger lattice spacing, going from the red to the green is the fully corrected result, there's a huge jump, okay? And the key is we have a formalism to make that correction, okay? So instead of extrapolating from this red point to the continuum limit with a very large extrapolation, which would give a larger systematic uncertainty, we can do some corrections for these unphysical effects to go to the green points. And you have a much shorter extrapolation to go, which is kind of nice. Now, these data points on the right are taken at nearly the physical quark masses. And so that's why I only list finite A and finite L as problems here. Okay, now this will become more clear in the second half of the talk, but in order to talk about how we create a formalism that makes this work, I need to talk more about the Dirac Lagrangian. Okay, and so you've heard a lot about QCD, and now I'm going to be a little bit more explicit, and I'm going to throw in some little exercises that you can do, not right away, of course, just to see how much you can understand of this. And now this is the Dirac Lagrangian in Euclidean space, which is how we simulate on the lattice, where this d slash, you may or may not know, is the sum over mu. Mu is going to run from 1 through 4. Okay, 4 is our time direction in Euclidean space, of gamma mu times the derivative in that direction. Okay, so we have a kinetic term, and I'm writing this in terms of the left and right-handed quarks. Okay, and that's going to be important shortly. And again, right now there's going to be a lot of theory coming up, and I'm not entirely certain of of everyone's background. So if there's anything you want me to clarify, please holler. And if you type a chat and I don't respond to it right away, that means I didn't see the chat message. So unmute yourself and holler at me. So we have this kinetic term with the derivatives, and then we have the mass term. Okay, where this F is going to run over the different quark flavors. These gamma matrices are important because notice they're not diagonal. Okay, what they do in this expression up here is they mix the different spin components of the fermions, right? A single Dirac fermion has 4 components. It has a spin up particle, a spin down particle, a spin up antiparticle, or a spin down antiparticle. That's one way to interpret it. The way we're doing it, the way I've written it here, is we have right-handed and left-handed states. Each can be spin up or spin down. Okay, and so this is called the chiral basis or the Weyl basis because we care about the handedness, not the particle-antiparticleness. But either way, there are 4 states, and these gamma matrices are going to mix them all together. Okay? And so I put these up here for later exercises that you can do on your own. And since they're not diagonal, notice none of them are diagonal, then all of the different components are going to run around with each other. Now, what we can do, and this is a theory that has been known since the late 60s, early 70s, is study what's known as chiral perturbation theory. And what's nice about chiral perturbation theory is that we've seen and we've said that you can't study QCD perturbatively. You can't use perturbation theory for QCD. But that's if you're looking at perturbation theory in terms of the strong coupling constant, which is very large. However, chiral perturbation theory is basically a low energy effective theory, which allows you to study the most important states of QCD, which is the lowest mass states, as an expansion in their energies. And so this is really useful for when you're looking at the pions and maybe even kaons. Any of the lightest particles that involve up and down quarks for sure, and then maybe the strange quark as well. And what's great about this theory is that it allows you to have a formula to truly understand all three of these errors. What errors? Well, the ones I've been talking about. Finite lattice spacing, finite volume, unphysical quark mass. So let's talk about this, ignoring the finite volume and finite lattice spacing stuff, and just talk about what we would call continuum or ordinary chiral perturbation theory. So again, we have this Lagrangian here, and notice that I've sort of highlighted two different sides. And I know you had a little bit of discussion of group theory on Friday with Chris, so I'm just going to assume you're all perfect experts in group theory. It doesn't matter too much the exact details, but if I look at each of these terms, the first two terms in the kinetic part of the Lagrangian, they only involve left-handed quarks together or right-handed quarks together. So this has a separate symmetry quarks, and it's an n-dimensional symmetry, SUN left. So if I change the fermion field by an SUN matrix L, and of course psi bar will change by psi bar L, and then I could change the right-handed quarks separately. L and R on the left-hand side over here are different, be the same. These two terms are invariant under this chiral symmetry. This is called a chiral symmetry because it's talking about the left-handedness and right-handedness of the symmetry. The latter two terms involve the quark mass, and they mix left and right-handed components. And that's because when a Dirac fermion has a mass, then it doesn't, the handedness is ill-defined, right? The handedness you can always remember by put your thumb in the direction of the momentum of the particle, and if you can use your right hand to allow the spin of the particle to wrap around it, that's a right-handed particle. If you need your left hand to wrap your fingers in the opposite direction, it's a left-handed particle. But for any particle with momentum is ill-defined, right? Momentum to the left, as long as I do a Lorentz transformation, I could boost such that something moving to the left is now moving to the right. But the spin stays in the same direction. And so a left-handed particle in your frame might be a right-handed particle in mine. And that's something that we can see mathematically in this expression right here. So instead of having a full chiral symmetry of SUN left cross SUN right, we have the vector subgroup of that theory, of that symmetry. In other words, as long as I transform the left and right-handed guys by the same SUN matrix, V, then it's a symmetry. But the full chiral symmetry is not a good symmetry for the mass term. Okay. Now, what that means is that what we would expect is that there are certain quantities, one of which I'll put up on the next slide, that should vanish if this is truly a perfect symmetry. And that one quantity we'll talk about is called the quark condensate. And I can write the quark condensate as the expectation value of Q bar Q, which involves the right and left-handed guys here. And if I look at this, right, if I take this, and I'm writing this as Q instead of psi, same diff, okay, from the previous slide. So if I look at the individual components of Q bar Q here, J and I are referring to the different quark flavors, then under the chiral symmetry, this would transform to this. And so if the mass is 0, this expression here on the left-hand side should be 0. Because under a transformation, it's not invariant, okay? Just like you know that if you have a good rotation symmetry, then a term that only depends on the y direction should vanish, because if you have perfect rotation symmetry, then nothing should have a preferred direction. Same thing here. But we see that, in fact, this quark condensate is non-zero. And so somehow this symmetry is spontaneously broken, okay? And so if you have a spontaneously broken symmetry, then you can write this operator in terms of some sort of object, I'm going to call it sigma, This is a different sigma than the correlation matrix from the previous lecture. And this sigma is going to contain, with a little bit of analysis, you can see that it's going to contain the lowest states of QCD. Pions, if you're only dealing with 2 quarks, maybe the kaons. And under the chiral symmetry, this sigma must transform like this. And so what I can do is construct a theory that actually is invariant under this chiral symmetry, but has this feature of this spontaneous symmetry breaking of the quark condensate being non-zero. And what you find upon analyzing this theory is that you get this expansion in momentum. Okay, you get a Lagrangian that I can write in terms of what I'm calling L2, L4, L6, and we can all count by 2, so 8, 10, 12, where the subscript corresponds to the order in momentum that term arises. Now, I'm not, again, deriving that or explaining that. You can find some really nice lectures out there. And if anyone's interested, please do email me and we can discuss more about it later. Just avoid the Wikipedia article on this. It's just horribly incomplete. The leading terms actually look like this here. Okay, this one term, remember sigma is a 2 by 2 matrix, for example, if you're talking about SU2. And so this first term is invariant under the SU2 cross SU2 symmetry, but it actually has states in it. In fact, if I ignore this second term, so right now just cover up the second, I was about to do it myself, but you can't see my hand. Cover up the second term, and if I look at this, this actually describes a theory of 3, for SU2 anyway, Goldstone bosons. And what Goldstone proved was that for every spontaneously broken symmetry you get, you will have a massless scalar boson in the theory. In this case, when I look at SU2 left cross SU2 right being spontaneously broken to SU2, I have 3 broken symmetries. And those are the 3 pions, the pi plus, the pi minus, and the pi naught. So we get those 3 Goldstone bosons. And of course, we don't have massless QCD. The quarks all have masses. And this second term is a way to incorporate the non-zero mass term of the quarks. And so let's assume that the up and down quarks have the same mass. Okay, so this capital M matrix is just little m times the identity. Then you can easily expand these out and show that the pion mass squared should be proportional to the quark mass. Okay, this is limiting for phenomenology. You can't change the quark mass, right? The quark mass in nature is just the quark mass. And the problem with this prediction is that mu and f are low energy constants that are unknown unless we could solve QCD. And if we could solve QCD, we wouldn't need this. Now, a little exercise for you would be to use this representation of sigma. That's why you should download the PDF that I sent out, which is the exponential of the pion field. So you got these pi's, those are the 3 pion fields, times the Pauli sigma matrices, and you can look those up, divided by this f, and if you expand this out to quadratic order, you can show that this Lagrangian here would in fact give you this prediction, assuming that M here is just a diagonal matrix with the masses. Okay? So again, it's a nice little prediction, but how useful is it? Well, it actually becomes messier and more useful when you include the L4 terms. Okay, so the first 2 terms in this set of equations here are just the terms that I showed right there. The next 3 lines are 8 of technically 12 additional terms at order p to the 4th. So these are all the different terms that come into play, and it gets messy. In fact, for every order in chiral perturbation theory that you take your Lagrangian to, the number of terms gets larger and larger. L2 in this case has 2 terms. L4 has around 10 terms. L6 has roughly 100 terms, so you can guess what L8 would have. It's very complicated very, very quickly. But what we can do is we are able to couple this. So this is an effective theory of QCD. We could couple this to QED. We could make the pions have charge. And we'll do that later, or at least I'll discuss how we've done it later. And this actually can give us lots of predictions. Okay. So for example, let's say we want to look at the pion mass squared beyond that term that I just showed you, that 2 mu m term. Okay, so that's what this 1 looks like, 2 mu, and I'm writing this as m sub l for the light quark mass. You actually get this more complicated expression. Now this is using all of these terms here in this box that, that are non-zero. So you see on this slide, I'm going to go back and forth to make you dizzy, these constants, L4, L5, L6, L8, are appearing on the second line here. Okay. And remember, of course, in nature, we can't change the pion mass. We can't change the quark mass values anyway. But on the lattice, we can. And in fact, we often will have to, because computationally speaking, it's more expensive to decrease the quark mass. Now, just a couple of terms here, and I should have circled both of these. Whenever you see a term that looks like m squared log m squared, that's what we call a chiral logarithm. And the reason it's called that is because the log part wants to diverge as that mass goes to 0, but because of the m squared out front, this whole term does vanish in the chiral limit. When the mass goes to 0, this term will vanish. These terms down here are often referred to just as analytic terms because they don't have logarithms. That's really all it is. Okay. And one thing that I want to point out, and let me get rid of that for a sec just so we can see these analytic terms better. I could have written this a little bit more condensed, right? Because you have there's this 2 ml bit here and a 2 ml in that second term. The reason I don't is because the origin of the first term and the origin of the second term here is very different. If you recall, well, when we're doing lattice simulations, there are sort of 2 kinds of quarks that are in the simulation. There are quarks that you may use to generate the gauge field configurations. Those are called C quarks. But those do not have to be the same quarks that are used to generate correlators, like the pion correlator. So of these analytic terms, the second set of terms, with the L6 and L4, actually only involve C quarks. The first term here only involves the valence quarks, the ones that make up the pion we're looking at. This is just an aside. You don't really need to know this, but I'm just pointing it out just to be complete. So we can use this, right? And so let's look. I'm looking at that old data from 2004, but now instead of looking at the pion decay constant, which by the way, there is a similar expression for the pion decay constant for that old data that was used. But instead I'm going to look at the pion mass. And again, we're in these weird system of units with these R1s. These are dimensionless numbers. Don't worry about what they actually mean. All that matters is these different data points that you see are unphysical quark masses. Okay, the physical quark mass is somewhere around here, I think, if I recall correctly. Again, this is very old data and it's out of date. But what you can do is say, well, to a first approximation, this does fit to a line, right? I can see that easily. And therefore, I can say, okay, well, the pion mass squared is linear in the quark mass, and I can determine what this mu parameter is. Okay, so what is normally done is you do a first pass of fitting to get an expression for mu, and then later you can put in this full expression here in order to get a better fit for all your fit parameters. Okay. continuum chiral perturbation theory. So now this is that same plot, but with all the data put back in. I took out, notice, a lot of data to make it a little bit more legible. But where are all these pions coming from? Notice I've got all these pions with different indices on them, pi 5, pi 0, 5, pi I 5, pi ij, and so forth and so forth. In fact, there are 16 of them because I runs from 1, 2, and over 1, 2, and 3. And so that's kind of messed up. So where do these other pions come into play, and why do they look like this? Continuum chiral theory, I should say, doesn't allow us, a little typo, rather important typo, it does not allow us to take into account, oh wait, no, it allows us to take into account chiral superposition only due to the quark masses. But in the continuum, we've got these, well, 15 extra pions. So where do they come from? So let's talk more about quarks on the lattice. Okay, and I know that Chris did not talk about this explicitly on Friday, so I'm going to give you a little background. In order to make sure that fermions have the proper statistics in the quantum theory, we actually have to describe them by Grassmann variables. These are anti-commuting numbers, okay, which I can't put an anti-commuting number on a computer, right? When you want to simulate something numerically, you have to use numbers that your computer understands, which means always commuting. You can't make 2 and 5 anti-commute. Luckily, most of the actions we use that involve the quarks are bilinear in the quarks. And what that means is that we can integrate them out analytically. And if you're familiar with functional integrals, then you'd be able to understand what I'm writing here. If you're not, don't worry, just sort of let it wash over you and absorb the glory that I'm putting up here. When you integrate this out, you get what's called the quark determinant. This is what's on the right-hand side. And I realize I've got 2 slides that are sort of out of order, but what are you going to do? Yeah, so I'm gonna skip half of the slide and come back to it. And so this is our quark determinant, okay, for our theory, and it describes the quark for us, the quarks floating around, okay. Well, I'll go ahead and state this. Suppose, though, let's say this were a theory with 16 degenerate quarks. So we had, for some reason, 16 quarks that were all the same mass. Then this determinant right here, which would be one that describes 16 degenerate quarks, you can show that this would be equivalent to the determinant of a single quark 16 times, so raised to the 16th power. Okay, and again, this is something we can prove, but I'll just let it slide by for now. Again, if you're familiar with field theory, you'll know what that means, and if not, then just sort of hold on to that as something we're going to need later. But here's the weird part about quarks on the lattice. There's a weird symmetry that arises in our theory. Because if I take my fermion field, psi, and this is for a single quark, let's say it's an up quark, and I multiply it by this matrix here, so this phase factor, e to the I pi x dot p, times this capital gamma. This capital gamma is basically a product of those gamma matrices that I've talked about. This p has one of 15 possible values. In lattice units, this p is basically a 4-vector with ones or zeros, all except for the one where you have all zeros. So you got 1, 0, 0, 0, 0, 1, 0, 0, and so forth and so forth. So there are 15 of these 4 vectors. Obviously, if AP is equal to 0, 0, 0, 0, yeah, that was right, then this gamma matrix is just the identity, and there's nothing interesting going on. But what this means is that because our discrete version of the theory, not the continuous version of the theory, not continuum QCD, has this symmetry, then if we have a fermion which satisfies the lattice Dirac equation, then there are 15 other solutions labeled by this psi p, right, where I can make this transformation, which all have the same mass. So another little exercise for you to do is to take those gamma matrices that I plugged in and plug it into our discrete lattice action, which I'm going to put up on the next slide. Now, the problem is, well, I'll put them on in a couple slides. The problem is, of course, we don't want all these extra doublers. Okay, and I'll explain where they're hiding shortly. So the question is, how do we get rid of them? And there are lots of methods. We're going to talk about one of them, not the others. But again, just to sort of give you an idea of what all is out there, I want to sort of discuss them all. So we have Wilson quarks. These tend to be slow. Okay, it actually breaks chiral symmetry at finite lattice spacing, and so it's tricky, but it's really nice because it gets rid of all of those doublers. We have staggered quarks, which is what we're going to talk about today because, well, that's what most of my academic life has been spent with. They're actually a lot faster than most other methods to simulate. They have a remnant chiral symmetry at finite lattice spacing, which is a good thing. But there are still 4 remaining species in the continuum limit, which is not good. These other two methods, domain wall and overlap quarks, are much slower, but they're very good theoretically. They're really nice with the chiral symmetry and getting rid of all the doublers. But let's talk about staggered quarks, because those, as I said, are the most interesting for sure. Okay. So let me, oh yeah, I got to actually hit forward, right? I'm just glancing at the time. So we're about halfway. Good. Now, why do we have these doublers, and how can we use that reason to, well, get rid of them? Well, or at least some of them. Well, on the lattice, we don't have rotation symmetry anymore, right? If I imagine a vector connecting 2 lattice points, then I can't just rotate my arm in any direction. I can't rotate by 30 degrees or by 2 degrees. I can only rotate by 90 degrees or by 180 in any given direction. I can flip it. So the normal SO4 rotation group, which is the rotation group in Euclidean space, is broken to only allow hypercubic rotations. And what that means is that I can actually diagonalize my gamma matrices. If I do the following transformation, right, the gamma, and this is, I thought I had updated this this slide. Stupid typos. If I take my gamma matrix, this should be gamma 1, gamma 2, gamma 3, gamma 4. Okay, not gamma 1, gamma 1. The gamma should correspond to the value of x, the component of x that I'm multiplying by. Remember, x is an integer here, right? We can only live on integer units of the lattice spacing. So x is going to be basically 0, 1, 2, 3, 4. It's going to be even or odd. The gamma matrices, if you go back and look at what I showed you, all of them square to 1, to the identity. So basically, this gamma 1 to the x1 is either going to be gamma 1 or the identity. It's same with gamma 2 to the x2, same with gamma 3 to the x3, and same with gamma 4 to the x4. If I replace my psi by chi with this particular spatial dependent factor, and I look at this term with the gamma mu in it, that's part of the kinetic term of our Dirac Lagrangian, or Dirac action. A little bit of work, which again is a nice little exercise you can do, shows that this is just going to be a phase factor, we call it. It's going to be -1 or 1. That's all it will be, depending on what mu is and depending on what the 4 vector x is, times a 4x4 identity matrix. And remember what I said earlier, the gamma matrices mix the spinor components of the Dirac fermion. This means that this transformation decouples them. So the different spinor components of chi don't interact with each other at all. So why keep them all? Exactly. Why not? So let's get rid of them. Let's get rid of 3 of them. So instead of having 4 spinor components, we have 1. So now we still have this doubling problem. You're still going to get 16 doubled states, but they're 1 component, not 4 component fields. And actually, a little bit of analysis shows that you can identify those 16 single component fields as 4 component Dirac fermions, which we call tastes. Taste we use instead of flavor for up, down, strange, charm, etc. But we want to make sure that we distinguish the unphysical doubling from the lattice theory with the physical flavor of up, down, strange. And it turns out that these 16 single component fields are actually staggered across a 2 to the hypercube. That's where we get the name staggered quarks. And so, as I said, remember before, so what we're going to get is the staggered Dirac operator will actually look like a determinant that describes 4 quarks. And if they're degenerate, then I could write this as the staggered action or staggered determinant of a single quark raised to the 4th. And so what I could do is if I want to get rid of those remaining doublers, I could just take the 4th root of the quark determinant in my simulation, which is what we do. Now the big question is, are you allowed to do this at finite lattice spacing? Or rather, a better way to say it is, I know that for sure, if I take the lattice spacing to 0 and then take the 4th root of the determinant, everything is fine. But that's not what I'm doing. What I'm doing is taking the 4th root of the quark determinant and then taking the lattice spacing to 0. Do those operations commute? That's really the question here. And a lot of literature came out in the early part of the 21st century. That sounds weird to say. Between around 2003 and like 2012 or so, arguing on either side. Pretty much all of the theoretical and empirical evidence for what we're doing say that it's not a problem. So we'll assume it's not. And there hasn't been any indicator of it being a serious issue. So what's great is, and I won't talk about how you can do it, but you can account for this 4th root procedure in chiral perturbation theory. So it's all going to be nicely consistent. So now let's actually put up the action that you would get for staggered quarks. It basically looks like this. We've got the discrete derivative operator. Discretize the derivative however you wish. I prefer the centered first derivative, but you can use a forward or backward derivative. These are those phase factors I mentioned before. And this del mu is acting on, of course, chi sub x here. In the continuum limit, this should give us QCD. At least that's the idea, right? And what we can do is use the fact that the lattice action, and so this S lat is this S quarks, could be thought of as, or can be expanded about the continuum action. So this S4 is this guy right here. And it's like a power series in the lattice spacing. And if I can write out this action as this expansion, this is known as the semantic action, then these higher order terms in the lattice spacing could be used to introduce discretization effects into chiral perturbation theory. Okay, so that's why I did all this right here. The key is that all the symmetries in the lattice action need to be symmetries of each of these individual terms, S4, S5, and S6, and so forth. Okay. And so this is what was done around 2002 and so forth. But how do they arise? Well, I stole this nice image from Martin Savage to sort of show what these different doublers look like. This cone here, this is the Dirac cone in space at near p equals 0. And you've got this nice conical shape because of the nature of the momentum of the quarks. And if I take the Fourier transform of a cubic lattice, hypercubic lattice, then I'm going to get what's known as the Brillouin zone, right, in momentum space. And that's corresponding to these different values of the momentum being near 1 over a at different components. These different corners of the Brillouin zone are those doublers, okay? Now remember, we're not getting rid of the doublers with staggered quarks. They're still around. They're just single component doublers. So they still have an effect in our theory. And so here's a nice simple chart. Imagine I've got an up quark of 1 taste, okay? So it's in one corner of the Brillouin zone, and I've got a down quark of a different taste coming in, and they exchange some gluons of a very high momentum. Well, that means that this down quark now is going to change tastes. These are called taste-changing operations. And these are all over our staggered action. And so these types of 4-quark operators actually contribute to chiral symmetry breaking, because now we actually are changing the tastes of these different quarks coming into the picture. Okay, so basically exchanging high momentum will take this red coned guy and bump him up or her up to one of these other corners. And so what do you get? Okay, now we're not going to go through all the derivation. That would be an entire lecture on its own. What do you get as you, in order to understand all this? Well, you get this. The first 2 terms look a little different, but basically are the same as what we talked about before. These are basically your continuum chiral perturbation theory results. And then you get this, you can forget this third term here. It's not going to be really too relevant for what we're talking about. You get this additional, what we call taste breaking potential V, which has 8 terms in it. And they look beautiful. Now you're jealous. What's nice about this entire set of terms is that all 8 of these terms contribute to just 4 different values of this parameter I'm calling delta. And we basically, so, if I have 4 tastes of a quark and a pion is made up of a quark and an antiquark, that's why we get 4 times 4, 16 pions. Okay, and that's what all of these are, but they're lumped into 5 irreducible representations of an accidentally unbroken symmetry group. So you have the axial guy, this pi 5, or the pseudoscalar guy, the pi 5, these axial vectors, these tensors, these vectors, and then a singlet. And what's interesting is that this delta is 0 for this bottom guy, for the black line, and for the other folks, they're roughly equally spaced. Not exactly equally spaced, but roughly. Okay, and then these can be predicted from the staggered chiral perturbation theory. And I should be clear, rooted staggered chiral perturbation theory. We're using that 4th root guy. But again, remember, this fit here is just the first step. Again, I'm pointing at my screen. This set of fits is just the first step to get what these deltas are and to get what this mu is. The full expression of the pi on mass squared, remember, has all these chiral logarithms. Okay, and there are a lot more. So these 2 terms here, oh good, I can highlight, were the chiral logarithms from before that I showed many slides ago. This L of m squared notation is shown right here. Okay, L of m squared is that chiral log. And all of, oops, yeah, now that's going to get messy, but all of the terms along this first line, and notice it's actually twice as many as these, are all new chiral logarithms. And so again, just like as I showed with the pion decay constant, if you don't include these additional terms in the first line, you get a very bad set of fits. You're getting that confidence level of 10 to the negative 250. But if you include them, then all of a sudden your confidence level goes up tremendously. Now I want to point out that this is a simultaneous fit right here to 28 different data sets to this expression up here. Okay, because for every input quark mass, these pion masses and the atom masses, all those masses change, okay, are different. So we have to, all these different values of those expressions. This F here is a fit parameter. The mu is a fit parameter, okay, to get the full expression. These low energy constants, the L8s and L5s and whatnot, this C, which is unphysical, is a fit parameter. So except for that difficulty of inputting all of this data, so now imagine, right, the fits that you did earlier today, for those are for the delta and nucleon masses. If they're for pion masses and you have them for different input quark masses, you would get these data points as shown here. The curvature is much more clear. You know, in this form here, if I just plot pi m pi squared versus the quark mass, they look like lines. But if you divide out this quark mass here, you get that nice curvature that's much more obvious. Okay. And then of course this here, this vertical line right here is the physical point we would like to extrapolate to. So except for these little complications of a much more complicated fit function and the fact that you're fitting a lot of different data points, this is just like the kind of fitting you did before with the Leavenworth-Marquardt algorithm. It's just a much different fit function. And so as you can see, just fitting to get the mass doesn't mean you're finished your data analysis. You still have more to do. Okay. So what's interesting is what is not clear, I didn't make it very clear here, is that we can also incorporate finite volume effects here in the chiral perturbation theory. And I'll discuss a little how we do that shortly. So this is basically a fit that includes finite volume corrections, finite lattice spacing, and unphysical quark mass corrections, all within the context of this theory, chiral perturbation theory. Okay. And so now I want to discuss those explicitly, but let me actually pause because I've been blathering on for a while, and I just want to see, are there any questions about anything that I just discussed? So now I'm popping out the chat window. You can throw a message in the chat window or unmute yourself and ask a question. I'll wait for a minute.
Would you mind popping back to slide? It's pretty early on. It's a specific question. The one where you have like the symmetries of the Lagrangian and you have SU10, SUN-L and SUN right on the kinetic terms.
This guy right here?
Yeah. It didn't really affect too much in the future, but I missed what you said. The SUNV, what's the subscript V standing for?
It stands for vector. So when the left and right-handed guys are the same, we call them vector symmetry.
What do you mean when they're the same? Like,
so notice this expression right here, psi left goes to left, else psi left, and blah, blah. In this left-hand equation, L and R need not be the same. But if I make them the same, and I'm calling them V now,
I see. Okay.
then we call that a vector. So the left and right transformations are the same. That's what I should say.
Okay. So they're set. Kinetic terms are, you can transform right and left separately, but mass terms you have to same transformation left and right.
Exactly.
Right.
Exactly.
And then on the next slide, so this slide confused me a bit, and I'm not sure why because I got most of the rest. Could you go through this again?
Yeah, absolutely. Yeah, this is pause. So okay, now forget we have this at all. Pretend the mass is 0.
Okay.
So that this is our symmetry of our theory.
Mhm.
Because this is a symmetry, oops, Now I'm making a mess.
Yeah, I'm doing the exact same thing as you're doing that. I'm highlighting an equation and all the artifacts
I
are popping
highlight
up.
way too much when I'm on my computer. And so, so this chiral symmetry is a good symmetry, which means that if there's any observable that I could calculate that is not invariant under that symmetry, it must vanish. Okay. And so that's what this is sort of demonstrating. And actually, before I talk more about that, it's like magnetization is the perfect example of this. If you have a piece of iron that's not magnetized, normally the magnetic moments of all the different domains of a magnetic material, they're all randomly oriented
Mhm.
because there should be no preferred direction unless you turn on a magnetic field. So if I turn on a magnetic field, let's say up, then a piece of magnetic material will now have a magnetization upward because, well, I've broken the symmetry. Now, a ferromagnetic material, once I've done that, if I then take away the magnetic field, it stays magnetized in that same direction. And so I've broken the symmetry. I should not have a preferred direction for the magnetization because the theory without a magnetic field has no preferred direction. And yet it stays magnetized. So the magnetization of a ferromagnet is non-zero. This is an observable that should be zero if you have rotation symmetry. And so magnetization is an example of spontaneously broken symmetries. The symmetry of the theory is not apparent in the physical states of the theory. That's
Yeah.
what's happening here. That this object right here should be zero if chiral symmetry is a good symmetry, because if I take this expression here and make the transformation, I get what's on the right-hand side of this arrow. Because the left and right-hand sides do not equal each other, then this expectation value should vanish. But we see that it doesn't.
And when you say it's going to sound pretty dumb, I got all the spontaneous symmetry breaking stuff. The QQ bar is non-zero simply because, quarks exist and propagate with
Well,
non-zero.
this is an observable you can measure to see that it's non-zero. That's what I should say. I'm not even saying what this actual thing means. I'm just saying that this is something that ends up being non-zero even when the mass is.
Okay, that was I was wondering, how do we know it's non-zero? And then it slapped me in the face as we were going over it. You just, you look at it somewhere and you see that it's non-zero in there. Then you have a broken symmetry. That was what was confusing me.
Okay, cool.
Okay.
Other questions before I. Oh yeah. So is chiral perturbation theory the only way to get finite lattice corrections? No. The best way to get finite lattice corrections is to do simulations at multiple volumes or multiple lattice spacings. Then you can do an extrapolation, right? If I could calculate at 5 different volumes, then I could extrapolate an infinite volume. If I could do at multiple lattice spacings, I could extrapolate to um, 0 lattice spacing. But now notice, for example, this data set here, let me get to it again, the old data set. Gonna take me a sec. There we go. This set here, and just so I can still see the chat window, I'll leave it not full screen. This data set here is only 2 lattice spacings. So yeah, I would like get each lattice spacing and then extrapolate to the continuum. But if you only have 2 data points, you don't really know how to extrapolate. Similar, and these are certainly done at 1 volume, but we're incorporating finite volume corrections that we would expect to see. If I had 10 lattice spacings, then I might be able to. Chiral perturbation theory allows us to know how we expect the theory should approach the continuum limit. Okay, so in a sense, I don't know how to go from lattice spacing to 0 lattice spacing normally. And chiral perturbation theory gives me guidance on how to do it. In the end, you could just keep doing it for more and more lattice spacings or more volumes and eventually see an asymptotic behavior. The problem with that is that these are expensive that is streaming. In order to get all of these data points, and these are of course on much older. It took 5-6 years to get a full data set, a little less. And so for every time you change the lattice spacing, you're going to increase your computation time by a significant amount. And so while it would be nice to do an extrapolation, we need some sort of theoretical guidance. Okay. There are groups that don't use perturbation theory and just use various models, and you sometimes use easy and fitting techniques. But this has a nice, you're welcome. This has a nice theoretical basis behind it, which is why I like it. So let's one more pause before we keep going. All right. So volume effects. Imagine you have a pion sitting here on your lattice, okay, and I want to propagate that pion to this point. Well, because I put periodic boundary conditions on the quarks, there are periodic boundary conditions on the pions. And so I could get from this point to that point by this route or by that route. And that those should have come in the opposite order. Whatever. I could go around, I could wrap around the world, right? I can go this way, and if I walk out this side forward, then I'd come back in here. Now, of course, yes, you might be thinking you have to stay on the points. Fine. Don't worry about that. Obviously, the larger the volume, then the less likely you can wrap around, right? If the volume increases more and more, it's harder to wrap around the entire world. Also, because of the Compton wavelength of a particle, the heavier the mass, the less likely it will be able to propagate. And so you can do a simple analysis, and I'll show you some results from this shortly, that show that the differences between the finite and infinite volume results tend to scale exponentially in what we call M-pi-L. So a lot of times you'll see lattice results for configuration saying, oh, our M-pi-L is 4.2, or our M-pi-L is 6, or our M-pi-L is 2.5. Standard lore tells us that we really don't want an M-pi-L much less than 4 in order to minimize finite volume effects. Okay. Doesn't mean people don't do those simulations, but again, standard lore. So how do we incorporate them in our theory? Any integrals in quantum field theory that we have that are over momenta become discrete sums because, again, because of the different corners of the Breen and because of the finite volume, our nice Fourier transform become Fourier sums. And our momenta are discrete now. They're 2 pi over L times integers. And so we could just replace all of our integrals by sums. We don't want to just do that, and I'll explain why shortly. Usually what we like to do is to modify our results by using what's known as the Poisson summation formula. And this, if you have a sum over discrete integers, again, very simply mentioned just for simplicity, we can write this using the exponential representation of the Dirac delta function as the sum for all values of x, so it's a continuous integral now, times phase factor e to the 2 pi I n x, which I can write as two terms. I could write a sum of that same for n equals 0, which is this. The idea is that here's our finite volume calculation, which would be closely related to what we do on the lattice. This would be the infinite volume calculation, what we would in the infinite. Whatever's left over is what we call the finite volume correction. For example, those pion mass.
Your audio is cutting out a significant bit.
Okay. let's see. Let me just check my internet because that's often tricky in this room. Let's see. Is this
We heard all of what you said. It was just getting towards the point. It seemed like it was getting progressively worse. So
okay? So
it's okay now, which is
it's
strange.
okay now. All right, all right. Let's hope it stays okay now.
Yeah, it hasn't happened before. Maybe it's an artifact.
Okay, cool. But yeah, I'm glad you're pointing that out if it happens. It also makes me feel like there's people out there. All those chiral logarithm terms, the m squared log m squared, just get term. And so when I said that we incorporated finite volume effects before, this is how we, this K1 is the Bessel function of the second kind. And so this is basically an exponential. If I look at the first term here, it's going to look like minus ml over ml. And so this is very easy to calculate. Now it's very easy to apply to any calculation. So this is one simple way of applying the Poisson summation formula to calculations. So now let's talk about the anomalous magnetic moment of the muon. Okay, and I'm going to explain a lot of the figures that I had earlier in the presentation. And again, some of this you may not be familiar with if you haven't taken field theory, quantum field theory. Don't stress about it. I'm putting a lot of stuff on here just so that I'm being complete. But the idea is that that we want to calculate contributes to the magnetic moment of the muon. And we call it the anomalous magnetic moment, the G minus 2, because traditionally G should equal 2 in the original Dirac theory of the electron or muon. We G minus 2, even though we're really calculating G minus 2 over 2, but that's a minor detail. This calculation for higher order comes in at ordinary QED perturbation theory with several diagrams. This first diagram, any good first-year grad student who's taken a quantum field theory course has calculated. The second diagram, many students have not calculated, but it can be done in perturbation theory. But this diagram shows a photon that creates a lepton-anti-lepton pair, but it could also create a quark pair. This gives us a diagram over here, which I'm calling QCD. This is the most important term anyway, that involves QCD. It's still order alpha squared in the fine structure 37, but it involves some analytically. So we could calculate this QCD blob on the left. And the way we do it is we calculate this, what's called a vacuum polarization tensor. Okay, so imagine everything that you talked about on Friday by generating a set of gauge configurations. And now you take magnetic current, A mu, which I forgot to write on the slide, but you can look it up, and look at the correlation, the Fourier transform of this correlator. And that gives you this pi mu nu, which from must have the following tensor structure here. And again, all that you need to know about this expression is that what we want is pi q squared. Calculate is pi mu nu of q. And the problem is that, remember, momenta are discrete in a lattice. So look at the plot down here with the discrete momenta that I showed before. But I need to subtract off this function when q squared or k squared equals 0. But if q squared equals 0, this coefficient in front of pi of q is also 0. Whatever I calculate on the lattice for that point is utter garbage. So I can't access that point. Plug back into this integral, that integral I referred to earlier. I've got this f of k squared. That's where I get this peak around this point here. Well, I have to find a way to relate to q squared equals 0 to get pi. Plug it into this integral. Seems fine, but there's a problem. Okay. This is one of the things to point out, that even if you don't understand all of the I'm talking about right now, like physics, about that, think of fitting problems that I'm going to discuss, because that matters. So this here is a plot of pi of q squared, the red points, okay, with two possible fits. One, vector on dominance model, where A and B are the fit parameters, and M rho is actually not a fit parameter, that's a fixed number. The other one, is actually pi approximate. It looks like this model here, okay? If you look at this, they each use different numbers of fit parameters, but we're not going to worry about that. If you look at this by eye, which is a better fit? Well, they both look good. They both are within the uncertainties of the data points. That you might want to say that the dashed line is better, but and the dashed line has a smaller chi-squared per degree of freedom, 4 divided by 18 instead of 7 over 7. However, the dashed curve is correlated. It doesn't use any of the correlations between the different data points here that we would expect to exist. The solid curve does. Also, the Padea, and if you look up this paper, you can read, has, because of the analytic structure of the function we're trying to fit, it has a better theoretical trustworthy. So even though it has not a squared per degree of freedom, it's actually a correlated fit, which makes us trust it a little bit more. It also is not an ad hoc model, which is what this other formula is. They look similar, to be sure, but they're just slightly different. And here's the problem. The statistical fit looks better for the vector meson dominance model, but the values that we get for G minus 2 for these two different models differs by around 17%. This is a number we need like 1% errors on. So just try to think what would be a better fit. And the problem with any statistics you can do, you technically can't really say one is better than the other, at least not with the data that we have. So this is one massive danger with fitting, because you might get something that looks really good. This dashed curve has a really good fit. It gives us a really nice result, but there's possibly some hidden unknown systematic uncertainty because we're using a model. We're not using something that has a nice theoretical basis. So you always have to be careful. You can't just fit all willy-nilly. Now, there's another more recent approach to understanding the mu on G minus 2, which is called the time momentum representation. What's nice about this is you can actually calculate this pi 0 more directly, or at least this subtracted function, pi of q squared minus pi of 0 more directly, using this correlator C of t, much like the correlators we've been fitting. It's the correlator among these electromagnetic currents. Okay, and again, you can look up the expression for these. This gives me a function over time. And if I multiply by this particular expression here in parentheses, you can show that after summing over all time, this directly gives us the subtracted vacuum polarization. And so if I throw this into, so I take this correlator and throw it into basically this integral of W, or take this integral over the same kernel that was over here, f of k squared, now I'm calling it f of q squared, or f of omega squared. Stupid notation. Doesn't matter. It's just a variable. I'll calculate this expression here, w of t, and again, you can show that take w of t, multiply it by this correlator c of t, and then sum over time, I'll get this contribution to the vacuum polarization, or the G minus 2, rather, of the muon. Now, the problem is I've been doing a lot with chiral perturbation theory here, right? And the problem is that we can't actually calculate this correlator in chiral perturbation theory reliably. And there are lots of reasons why, and I can point you to several papers that discuss it. The main reason is that we're integrating over a large amount of energy. We're going from 0 to infinity. Remember, chiral perturbation theory is a low energy theory. This integral uses all energies. PT is not a good fit for this. However, because of the finite volume of can use chiral perturbation theory to study the finite volume corrections, because the finite volume corrections are by its very nature a low energy effect. Okay, this is when it came out. You can look at the electromagnetic current in terms of the pions, which is right here. And you can tell this is where I got a little lazy, not generating new equations. I just copied them from the paper. And we can then calculate this explicitly, right? Which is what's on the bottom left. This is actually to 2 loops, not 1 loop. The 1 loop term is this one. The rest of these 2 loop terms doesn't really matter. Most of you are going to forget that anyway. What matters though is this is not a good way to represent the correlator on the lattice. But what we can do is compare this to the finite volume or the infinite volume version using the Poisson resummation formula and calculate delta A mu, which is the difference between the finite volume version, which is this, coming from plus expression, and the limit, the infinite volume limit, which again we can do by sending L to infinity in this expression. So we can calculate this expression here in chiral perturbation theory and add it to the lattice the same quantity. And if we do that, we should get the infinite volume contribution. And what I'm not showing here is you can incorporate staggered quarks into this as well. But I'm just going to scoot on by that right now. So this is, again, a plot I showed earlier in the lecture, or in the day, or whenever. I don't even know what day it is anymore. And again, these are a bunch of numbers. You don't have to worry about them all explicitly. I put on top of each column what icons or what symbols correspond to in the plots. The blue points are the direct lattice values. From that, we can add in volume corrections directly, which shift them up a little bit. Then we add in, using chiral perturbation theory, what brings us from the red points to the black point. Okay. And then a little bit of rain, because the pion masses weren't exactly right, brings us down to the green curve. So basically going from the blue to the green curve is done by primarily chiral perturbation theory from that expression I showed before. And what we find is that after all this corrections, that there's still roughly a 4% uncertainty coming from leftover finite volume effects we couldn't account for. And this is important to understand. We need like 1% uncertainty in the theoretical number in order for this to be a viable way to search for new physics in the standard model. Okay. So I'm going to go ahead and sort of conclude, and then of course we have plenty of time for questions. So, and hopefully I'll have a bunch, because hopefully I confused you a lot. Sort of concluding the whole day, or at least up until the next lecture you all have. That hopefully you've learned an appreciation for the delicate nature of fitting, the painstaking process of fitting your results, and also for the fact that just because you fit your results doesn't mean you're done, right? Just because you got a mass out of your correlator or got that coefficient in front of the exponential in front of the correlator doesn't mean you're finished, because you still need to understand what that means, right? And so while this last lecture was a lot of theory, right, hopefully it gives you an appreciation for the fact that we need a lot of this theory to be able to understand the data, because we can't just say, oh, the data says this, this is what it means. Um, there are a whole host of other things that we can look at. There are unphysical phases in lattice simulations that could pop up that you using chiral perturbation theory method. Never just CD. I'm not sure why. Maybe you're a little crazy. I don't know. Or maybe you're crazy if you are interested in it. I'm not really sure. But even still, even if the exact details of what I talked about are not relevant to you, you need to understand the errors in your results. Even numerical results, they have errors. There are numerical errors, round-off errors, statistical errors, and then there are systematic errors when you're trying to connect to real physics, to the real world. And so even if the exact theories I was talking about today don't apply to you and what you're doing in your research, there is a theory out there that will apply to it. Okay. So thank you very much for paying attention and for doing the work that I gave you. And let me go ahead and say, are there any questions? We've got about like 5-7 minutes left. So how does KPT's estimation of finite volume effects compare to a direct perturbative or normalization group treatment of integrating out small momenta? That's a very good question. So basically, looking at a perturbative or normalization group treatment of integrating out small momenta. I will say that I do quite know. I'd have to look into if anyone's looked into that, and I'm sure someone has. But if not, could think about how that applies. It, yeah, I don't think that has been done, but yeah. So chiral perturbation there is low energy or long distance. Yeah. Um, so, but as far as the size of our lattice normally. And ideally, Poisson formula will allow to extrapolate to move beyond that. So it might work out that it'd be a similar treatment ultimately, but I have to think about it.
Question on the staggered quarks. Can you go back
Yeah.
to the, I think it's slide 19? Uh, the one with the chain of gamma 4, gamma 3, gamma 2, gamma 1.
This guy right here.
Yeah, your connection dropped, so it's not sharing your screen, but I assume you're on it.
Okay.
So
Let me. What I'll do is I'll stop sharing and I'll start sharing again.
yeah, that might work,
Go
just so
ahead.
everyone can see.
Come on. Let's see here. Is it sharing it now?
It isn't. It's still on the last slide. Oh, wait, it jumped. Now it's a white screen. I can see a browser window.
Is it there now?
You're starting to share content now.
Well, just
Anyway,
share.
yeah, sure. So what's the significance? So since we're on the lattice, we're allowed to consider rotations only in these four directions. Like we aren't forced to construct a theory that's invariant under like halfway rotations of halfway between the axes.
Well, you could create any kind of lattice structure you wish. A hypercubic or cubic structure is simplest, and that then forces you to only look at these 90-degree rotations. Um, and there are sort of theoretical reasons why that ends up being a lot simpler in other cases. because of other issues that arise in these lattice simulations. And so you're not forced to hold on to the full rotation group or to include more. You could create a theory that has more rotation saved, but you're not required to.
Oh, okay. I guess I should say this then. It's the important thing about it being hypercubic only is that x1 is either 0 or 1.
Exactly.
Gotcha.
Exactly.
Okay.
And so
And
yeah,
then
so
oh, go.
no, go ahead.
It's about the next line. So if you had a comment on that,
So I'm gonna say that
on
yeah,
the
so
previous line.
it'd be a little bit more confused. It'd be a little more complicated to see what the symmetries would be for a different lattice structure. But the most important point is that in the continuum is a continuous variable, so this expression doesn't meet. Okay, so yeah, and then your next question
Okay.
on the
Yeah. So when it says you decouple the 4 spinner components, so this identity here is only for the gamma mu, which would be in the like the partial slash term. Only in the kinetic term would you have this, right?
right,
Is
and
that an issue in the mass terms where you don't, or what?
no, yeah, so the mass term
Actually, it might square to 1 in the mass term as well. I don't know.
yeah. So in the mass term, this all squares to 1, and so it doesn't change.
Oh yeah, what am I talking about? You have gamma ones on the. I was thinking it was a flipped like 1 2 3 4 and then 1 2 3 4 again,
Right. Yeah. And
and it
so
wasn't
in the
immediately like
math
that.
term,
Okay, yeah.
nothing changes, and they weren't coupled, and they aren't coupled now. Yeah.
Okay, that makes sense. Yeah, I was just misreading the order of that.
Yeah. No problem. And then so Travis asks, why are discretization effects of time examined? And I did mention that earlier. Um, Generally speaking, historically, we like to use a larger value for the time direction than the spatial direction. If you look at any lattice simulation, generally you'll have, say, a 28 cubed by 48 lattice, or 32 cubed by 64 lattice. So generally the time direction is sometimes 2 or even 3 times longer than the spatial direction, which means that there would be some finite volume effects from the finite time direction, but they tend to be notably smaller. There are cases where we do examine them, um, but a lot of times when if you're looking at a fit function in time anyway, then that the how the often are taken care of there. But I should say that there are cases where some some observables actually have significant finite time effects that will arise. They just tend to be much smaller, and so usually they're neglected. Should they be? That's a good question. You're welcome.
Question on the taste changing.
Yeah.
I'm just a little confused since so I get how if you have a really high virtual gluon that you can kind of get bumped from the center of the Brillouin zone out to the edge where you normally think of the staggered fermions momenta being.
Right.
I'm a little confused about like does the momenta doesn't define the taste though. That's what I'm getting mixed up on.
So it actually sort of does.
It does.
In this
Okay.
case, yeah. So really, a single taste would be defined as having a maximum momentum of roughly pi over 2a, and so in a given direction. And so um, the big problem with the doubling issue in lattice QCD is that if a lattice fermion has a high momentum, you would think that that would correspond in the continuum to a fermion with a high momentum. But in
Mm-hmm.
fact, a fermion on the lattice with a high momentum corresponds to a continuum fermion with a low different momentum. And that's where the doubling arises. The key here with the staggered quarks is that you're actually, when you go to a different corner of the Brillouin zone, you may actually keep the same taste that you had before, but change the spin. Because it's all 16 components of the spin and taste are spread out throughout the Brillouin zone that way. But yeah, a high momentum actually changes the actual taste of the quark or spin. It's a very bizarre thing.
Okay, yeah, it's a non-intuitive.
Yeah, not at all. This is where even though staggered quarks are faster to simulate, they're much more complicated theoretically to understand. And the group theory gets more and more complicated as you try to work them out, which is why a lot of people hate them. So. Any other questions?
See, I think I'm gonna end recording now.
Okay.